Okay, good morning. I hope you had a great Sunday and a great Saturday afternoon. And we're back. As probably you've noticed, I was not the person that was announced in the original plan. So Bikshar couldn't come. So I'm doing the emergency replacement for him on this lecture, introductory lecture about deep learning and neural networks. Okay, so maybe I'll start by explaining why I have quote unquote neural. It's because I hate the expression neural networks, because I think there's nothing neural about neural networks. There's a vague inspiration in the beginning, as we will see, but nowadays, especially in the age of transformers and attention, that connection is completely lost. So, but still, we still talk about these things as neural networks, and I won't be able to avoid it. So this is. Anyone in the audience knows how to mute an iPad? No. It's okay. I can. Can you hear the iPad? A little bit. I mute it, and it goes back to tick up.
Oh, you have this button where you mute.
It's here. Hello.
Nothing. E baixar o som ao iPad.
Está no mínimo. Tá, ele vai ao zero. Okay, let's not waste any more time with this. Okay. It's better now? Okay. Yeah, it is. Okay, just a brief outline of what we will be covering today. So, just an announcement. The slides of Saturday and these ones are being shared as we speak, and they'll be available in 5 minutes, I guess. If anyone wants to take notes on the slides while we go. Okay, so I'll start with a brief history of deep learning or of neural networks, but I will stop before large language models. Okay, I will not talk about large language models in the history, only I'll go up to maybe 2018 or something, 2019, not even that recent. Then I will spend some time looking at how models of natural neurons gave rise to the inspiration for artificial neural networks. Then we become a little more technical, and we'll talk about deep learning, essentially via empirical risk minimization, which is a standard way of learning, of doing deep learning. We'll talk about gradient descent, stochastic gradient descent, backpropagation, autodiff. We'll talk about the most advanced optimization tools, like Adam, which is the sort of the standard thing. And then the final part will be specifically about convolutional neural networks, CNNs. And then we'll conclude. Okay. Well, let's hope this time I can cover everything. I'm a bit less ambitious than I was for Saturday. Actually, Saturday I was not too ambitious. I was just going too slow. Okay. So brief history. In my opinion, the deep roots of deep learning go back to Norbert Wiener, who in 1948 wrote this very influential book called Cybernetics, which has this amazing subtitle, which I don't know if you ever read. Although this one has oh, it's okay, yeah. A study of vital importance to psychologists, physiologists, electrical engineers, radio engineers, sociologists, philosophers, mathematicians, anthropologists, psychiatrists, and physicists. So understanding how the world works and how complicated systems that involve control and communication, which of course modern machine learning techniques and AI are, started in a formal mathematical way with Norbert Wiener in the 40s. I love to tell this story, so I will easily take too long here. And then it was very instrumental in the early days, because he was the person who hired McCulloch and Pitts for MIT. And McCulloch and Pitts in 1943 created the first mathematical model of how a neuron works, which we will see in more detail later on. So this is work from the early 40s. This is 1943 is actually during the Second World War. And in the next decade, so in the 50s and early 60s, Hubel and Wiesel used McCulloch and Pitts model to create a formal mathematical explanation of sort of an engineering explanation of how the visual system of mammals work. And for that, they won the Nobel Prize. I don't know when, but in the late 60s or in the 70s. Okay, so early machine learning. So one of the reasons why Norbert Wiener, who was the creator of one of the creators of mathematical theory of control, is instrumental not only because of McCulloch and Pitts, but also because he created the notion of feedback control, which was already known since the steam engine, but which is sort of the key idea behind modern machine learning, is feedback, is compute the error and use the error to adapt the system, to change the parameters of the system to make it a little better. And that's exactly what the control is all about. And the first actual implemented instance of machine learning is the perceptron, 1957, by Frank Rosenblatt. And a few years later, there's another version called Adeline by Hoff and Widrow. Hoff and Widrow were actually the inventors of stochastic gradient descent. So the things have very, very early roots in many years ago, like more than 60 years ago. And so the McCulloch and Pitts neurons, so the perceptron is essentially the idea of marrying together the McCulloch and Pitts neuron, which is a very simple model where you have a linear combination of features, like we saw it was a linear model, like we saw on Saturday, together with this idea that you should have a training set, examples, and if the examples are incorrectly classified, you feed back the error to the weights and change them. So this idea was essentially what the perceptron is, and it's still what machine learning is all about today. So this was the beginnings of artificial neural networks, the beginnings of machine learning, and this error feedback or error back propagation, how it's called these days, is still the core of modern machine learning. So all of modern machine learning is about how to learn parameters of these huge models, or almost all about it. And so it has these roots in the late 50s and early 60s. So what happened in the next 4 decades? Actually, there's a kind of inconsistency between, I say 4 decades, and then in the slide it says 3 decades. But so we started in the 50s with Frank Rosenblatt. Then in the 60s and in the 70s, nothing much very super visible happened. But in the 80s, we have Hopfield and Sosnovsky and Hinton and all these people starting to work on artificial neural networks. And as you probably all know, John Hopfield and Geoffrey Hinton won the Nobel Prize in Physics last year for their early work on inspiration from both from statistical physics and from neuroscience to create some sort of artificial neural networks, which is actually not the ones that are most used today. Which was a very important moment for all of machine learning to get 2 Nobel Prizes. To people getting the Nobel Prize. Of course, other very important names in the field are here, but one of them, of course, is Jan LeCun, which you probably, I'm sure you've heard, who was one of the early pioneers of convolutional neural networks, inspired by Hubel and Wiesel's work on the visual system of mammals, and arguably the first commercially viable product using neural networks learned. Actually, convolutional neural networks was this system to automatically. When it's PowerPoint, I have this. This is a video, but on PDF it doesn't work. It's a system to automatically read handwritten checks that when Jan LeCun was working for AT&T, and that is sold to many banks. It was sold to many banks, well, not him, but AT&T. And so this was probably the first commercially impactful application of machine learning of this type of neural networks. So all of modern machine learning is essentially about this idea that we go from this picture above, which is what we saw on Saturday, where we want to say classify an image as being a cat or not. And there's this feature engineering that we talked about, and the features then are used by some traditional machine learning models, such as linear classifier, whatever. And modern machine learning, deep learning, is about you do everything in one fell swoop. So everything is learned from one end to the other end, including the feature extraction, and this is why it's called typically end-to-end learning or representation learning or all of that. So these deep networks that we will see today they typically learn this is just, of course, the toy picture, learn this hierarchy of features. So when, for example, for images, they start by learning very simple features like edges and local contrast structures, and then these are composed to build more sophisticated features, such as they'll start looking like eyes and ears and noses and mouths. And then there's even more complicated aggregations of these will start looking like faces. And finally, you have some face detector or a face classifier. And this idea is sometimes referred to as compositionality, in the sense that the features, higher level features are compositions of lower level features. So this is kind of a bird's eye view. So what is typically seen as the watershed moment for these kinds of models is something called the ImageNet moment. So I'm sure you've heard about the ImageNet moment, right? Who has never heard about the ImageNet moment? Just so everybody, some people, okay. So the ImageNet moment was in 2012 at CVPR 2012. So CVPR is the Computer Vision Pattern Recognition conference, big conference on computer vision. And where they had this competition, there's this paper, and there's this competition for image classification based on, I'll talk more in detail later about this. They have this competition, and in this case, which is a small version, they had this competition for classifying images into categories. And this version has 1.2 million images and 1,000 categories. Actually, those 1.2 million images are split into training, validation, and test, and so on. And on the right plot, on the right bars, what we see is the error rate for some criterion of performance, doesn't really matter. And what had happened in the previous years, so 2010, 2011, and then in 2012, this system called AlexNet, that's written here, what's shown here, just obtained, it made a huge jump from the 26% of the previous year to 16.4%, and the other bars are the other competitors for the same year. So it kind of blew the competition out of the water, and it smashed the previous results, and everybody started paying attention to these systems. And this has lots of interesting, I'll describe this in more detail later on. One of the important features of this proposal was, as you can see there in the middle, GPU implementations. So this was the first very successful application, very famously successful application of using GPUs to train deep neural networks or deep convolutional networks. What happens in the following years? So what happened at this moment was essentially that almost, this is a bit of an exaggeration, but not by that much. Almost everybody that was working in computer vision stopped what they were doing and they started working on deep networks. There was hundreds and hundreds of people, thousands of people working on how to extract features. And then they say, oh, no, we can learn how to extract features. And so that changed a lot. And in the following years, not many. So starting in 2012, so in 2016, the error rates were down by a lot. It was already like around 3%. In 2017, they're like around 2.3% with evolutions of these types of networks. And human performance is around, for this data set, is around 5%. So since 2015, these systems are outperform humans in category, in image classification in this data set at least. And the same thing was happening actually in speech recognition. So this of course is a toy plot, but that one on the right is not. So speech recognition has kind of reached a plateau. So what we have in the vertical axis are word error rates. So you have speech, and the goal is to transcribe speech into text. And so it was on the vertical axis is word error rate, and it kind of had stagnated. And around 2010, although it is not so visible as the ImageNet moment, people started using deep neural networks for speech recognition, and the performance started improving again. And we see on the plot on the right that around 2016, these deep neural networks outperformed human-level speech recognition. Also in machine translation. So famously in 2016, Google Translate moved from a classical approach using hidden Markov models and all that stuff to neural machine translation. We've had people in this summer school in other years, and we will probably hear something about this in a later talk. But this happened. All these companies that had machine translation systems moved to neural machine translation, and so this changed a lot, and the performance improved a lot. Of course, there's this very famous application of course also of deep learning in science. There are many applications of deep learning in science. One that became particularly famous was AlphaFold, which I'm sure you heard about it, which is the most important, according to a newspaper article in 2019, I think it's 2021 actually. It's the most important achievement in AI ever. Okay, this was before ChatGPT. So 2022 was ChatGPT. So 2021, it seemed that this had been the greatest achievement of AI ever. And as I'm sure you know, AlphaFold, or the people who created AlphaFold, received the Nobel Prize in Chemistry in 2024. So 2024, in terms of awards and prizes, was an amazing year for deep learning. or for neural networks, because we had Hopfield and Hinton getting the Nobel Prize in physics, and the people, namely Demis Hassabis, getting the Nobel Prize in chemistry for AlphaFold. Why did it happen now? Why not 20 years ago? Okay, so there's a lot of explanations. I could go off on a tangent in that direction. It has to do a lot with the business models of companies that decided that they needed to use machine learning to make money, namely social media, e-commerce, and companies like Google, who do a little bit of everything. And so what happened was that we had this creation of this environment that allows something which I think is very, very accurately described by David Donahoe in a paper 2 years ago as frictionless reproducibility. In no other area of science and development, we had this type of frictionless reproducibility in the following sense. If you read the paper with some methods and you want to try it, you can try it in half an hour. You go to GitHub, you download the code, you have all this framework. Ideally, so in any other field of science, it will take months or years to reproduce some scientific experiment. In machine learning, we have all these frameworks and GitHub where people share stuff, and Stack Overflow and Hugging Face and competitions in Kaggle. And there's all this infrastructure. There's Azure and Amazon Web Services and Google Cloud and all of that. So you have access to computation, resources, data, other people working in the same problems, which had never, it's astronomically more than ever happened in any other field of science or technology. So this accelerated the progress in this area very dramatically. Okay, having seen the story, let's go to business and see how these things work from the beginning. So starting the neuron model that I mentioned a while ago, the McCulloch and Pitts model from 43, is essentially what we saw on Saturday as just a linear classifier, okay, with a threshold unit at the output. So it's just the model is that there's a few inputs. Each input receives a weight. It's weighted by some quantity, 2, 4, -1. There's a bias that's added. Everything is summed and go through a threshold, and if it's positive, the output is 1. If it's negative, the output is -1. So this is an extremely simple model. This is the original McCulloch and Pitts model that gave rise that, but all the in the abstract model of neural networks, all the nodes look sort of like this. Okay, it's still just many of these things connected together. Of course, a word of caution, because real biological neurons are hugely more complicated. They're not just like this, not even close to this. Okay, they work with pulses. They have, it's very different. But they have this, as seen from very, very, very far away, kind of can be seen like this. And later models, as we will see, replace the hard threshold by much more general activation functions, which you will see like 3 or 4 of them. So this was the main difference. So now more formally, so what we call nowadays an artificial neuron is just this little unit that receives inputs, D inputs, let's say, weighted by some weights from W1 to WD. That is a bias term. And this linear combination of the weights times the inputs plus the bias is called the pre-activation. And then there's an activation, so-called activation function, which is some non-linearity, which is applied. So the activation function is this G here. Yeah, this G here, which is a non-linearity that is applied to the result of this linear part of the function of oops. So okay, so typical activation functions that are used today, just linear, nothing, or a sigmoid or hyperbolic tangent, or probably what's most used today, ReLUs, rectified linear units. So what do they look like? So the linear looks like this. It's not even interesting. It has, in a sense, it's not very interesting because you don't, if you compose several layers of modules like these with linear activations, actually the final result is just a linear function, because composition of linear function is a linear function, and so you don't gain anything with using it. But you use it sometimes in the output layer if you just want to estimate some value. There's more to the story than that just a composition of linear function is a linear function. It's true, but when it comes to learning, there are sometimes it's relevant to do it. sigmoid activation, which is, we saw it on Saturday. It's the thing that appears when we're doing a binary logistic regression, when which takes some real number, an arbitrary real number, and squashes it into the interval 0, 1, according to that function. And so because it is in 0, 1, it can be interpreted as a probability, although it's not necessarily a probability. It's positive, it's bounded, it's strictly increasing, this function. That's already said. And now it's now known, and it's theoretically known, that by composing layers of units with sigmoid activation functions, increase the expressiveness actually allows it to express any function that you want. We will see a theorem that tells that. There's another one that's quite used also, which is the hyperbolic tangent, which is kind of a slightly shifted and the rescaled version of the sigmoid. Instead of squashing the reals to the interval 0, 1, it squashes them to the interval -1 to 1. Okay, so it's no longer a probability, but it's related. It's as we see in this expression here, they're related. The sigmoid is 1 plus hyperbolic tangent of the argument over 2 divided by 2. So it's just a rescaling and shifting of a sigmoid and vice versa. Okay, it's still also bounded, strictly increasing, so on and so on. Okay, and finally the ReLU that I'm sure you've all seen, or most of you have seen, which is just a rectifier. So in electronics, this is called a rectifier, but in machine learning, it's called a rectified linear unit. It's non-negative, it's increasing, it's not upper bounded because it's linear on the right. It's not differentiable at the origin because there's this little sharp edge there. Arguably, it leads to neurons which are closer to biology because some of them will be actually inactive, because when the pre-activation is negative, the output is 0. So many neurons will be inactive. And it's extremely cheap to compute. Okay, you don't need to store these exponentials or a lookup table or whatever. It's extremely cheap to compute. You just need to compare and just with 0, and that's it. Okay, so what is a multi-layer network? So this is just what we saw now, it's just one neuron. So a multi-layer network, the key idea, as I'm sure you all know, is just to use intermediate hidden layers between the input and the output. Is to assemble several of these things, both in terms of layers. You create a bunch of them, you put a bunch of them in parallel to create a layer, and then you stack several layers to create the full network. So each hidden layer, as we saw in the illustration in the beginning, computes some representation of the input and propagates it forward. And the next layer computes a higher level representation of the input using these lower level representation of the input provided by the previous layer. As we will see, it increases the expressive power of the network. It's completely non-linear as long as you use some non-linearity somewhere. It's also called a feed-forward neural network. Yeah. That's it, what it is. However, so this comes, of course, this added expressivity comes with a very hard price, which is learning the parameters is much harder than in linear models, as we saw. So in linear models, learning the parameters is very easy, as we saw. It's just actually for regression, you just invert the matrix. That's it. You have a closed form expression. Or if you're doing a logistic regression for classification, we need to use some algorithm to optimize, but the problem is convex and smooth. It's very easy to solve. But in neural networks, everything is much, much harder in terms of optimization. So what does it look like? It looks like this, okay? So a very simple model with only one hidden layer. So there's a hidden layer, it's called H, that's H for hidden. I'm assuming it has, the network has several inputs, D of them. There's a bias term on the right here. This is the bias, right? There's these weights that connect each input to each of the elements of W are collected in a matrix. So we have this matrix that has D columns and the size of H rows. So we'll have that in a second. I'm assuming that the output can be whatever. And so the fundamental idea is that what's now very different from what we had before is that have this hidden layer here and that it's computing. So this is a little bit like we saw on Saturday. where these functions could be, for example, remember the radial basis functions, those little Gaussians that allow me to approximate a function. But now we're going to learn these functions rather than we're going to learn where they are and what the width is and everything, rather than just having them fixed. If this was fixed, if these functions in the hidden layer were fixed, if the weights were fixed, if these weights here were fixed, everything would fall down to a linear problem. And all we had to estimate was these W2 and these B2. But now we're going to estimate everything, all the W's and all the B's and everything, okay? Okay, so more formally, so the activation, so the hidden layer pre-activation, you obtain before you compute H, remember that each neuron has a value that is the pre-activation, that's a linear combination of the inputs, and then there's this nonlinear function that produces the activation. So keep in mind, pre-activation is before the nonlinearity, activation after the nonlinearity. So the pre-activation is just a linear combination of the inputs. And I have k neurons in the hidden layer. I have D inputs, and so I have this matrix W here. This thing here is just a matrix of size k by D, because it has k inputs, D outputs, so it has D rows, k columns. Okay, it's extremely simple. So this W2, W1 actually looks like this. It has D rows. Sorry. Well, this is K. This is K, and this is D. Okay, now it's correct. This is W1. Okay, this is gonna go away. Okay, so now the hidden layer activation, it just make these pre-activation go through these nonlinearity, component by component. So we're using this correct notation of using bold to represent vectors. So X is a vector, Z is a vector, G is a vector. They're all vectors. And G is a function that goes from RK to RK. It takes the K pre-activations and produces K activations by applying the same function to all of them, say a sigmoid or ReLU. Okay, so it's very simple. And finally, there's the output layer. The output layer, what it does, it takes all the hidden layer activations, weights them by multiplying by these weights W2, adding the bias. Let me remove this. Adding the bias. Why is oh, it's the cursor. The cursor was on the slide. Okay, where this W2 is just a k-dimensional vector because we have k activations that I need to combine. So I need k weights and O that's being denoted by O. Now using the correct notation, O is a scalar because it takes a scalar result of a linear combination and it produces the activation function. Okay, so it's important when we're dealing with this messy stuff with matrices and vectors and scalars and blah blah. It's important to use correct, precise notation to not get lost and to have a clear view of what we're doing and what we're dealing with. So if we put everything together in one expression, we see that we have, so the output of this network is something like it's the activation of the final layer applied to this linear combination of the activation of the hidden layer plus a bias. Okay, so this is just a compact expression for what this network is doing. Please interrupt me and ask questions if you have them. So examples of output activations could be, for example, just nothing, just a linear function, just identity. If you're doing regression, if you just want to predict a value, a number, so you just output the activation itself, the pre-activation itself, I'm sorry. Or you could be a sigmoid if you want to do binary classification and you want to interpret the output as a probability of 1, probability of that this email is spam or something. So the big difference from linear models is that now, so on Saturday with the linear models, we could have nonlinearity on X, that's easy. But now this is also nonlinear in the parameters, and that's where the difficulties come in. So all of this is nonlinear in the parameters because there's nonlinear functions applied to functions of the parameters. Okay, so everything in the output is nonlinear. So in nonlinear in everything. So this hidden layer is sort of a learned internal representation. It's not manually engineered. You're going to see how it's learned. There's no one saying that the neuron should have these and these inputs. Yep. Yeah.
Like a few flights. Here.
Here? Here.
Yes, like what's it like a single output?
No, I'm just showing an example with a single output. I'm going to jump to multiple outputs in a second.
Ah, okay. So, okay.
Yeah.
Uh-huh.
No, this is the simplest possible example of a non-trivial network is one single output, one single hidden layer. That's why I started with this very simple model. I'm going to add more layers and I'm going to include more outputs in a second. Okay, so single hidden layer, single output. This is the simplest. You cannot even call it deep network. It's not very deep, but it's slightly deep. Okay, now single hidden layer, multiple outputs. This is exactly the next slide. Now notice that we've changed the notation from O, which is not bold, to an O that is bold. Now, because it takes several values, several pre-activations, and produces several activations. I'm going to show you an example. For example, O can be just the pre-activations. This is wrong. Should be O, sorry. This is wrong. And this has been wrong for a long time. This is U, of course, not O. So if you're doing multiple regression, if you want to produce several values, the activation can be just nothing. Just you take the pre-activations and put them at the output. It's called a linear layer. Or if you're doing classification, one possible output layer could be softmax. You take the pre-activations and you make them go through this softmax transformation, and you produce a collection of numbers that are non-negative and sum to one, which you can interpret as being probability of the classes when we have C classes. Okay. So again, it's nonlinear in X, nonlinear in W1 and W2. This is all the same. And it's the same comment as before. So here it is. So now in the full generality, with more than one hidden layer and more than one output, this is how it looks like. In this case, it's not a lot more. It's only two hidden layers, but we can go on for as many as you want. And in this example, I will explain a little. There's a little inconsistency between the drawing and what's written in the drawing. So the expressions are exactly the same. Just now they are indexed. We have this indexation with the layer number. What we have is the pre-activation of a given layer L is a linear combination of the activations of the previous layer L minus 1 plus the bias at layer L. Okay, so what this thing here is saying is what each neuron is doing with the outputs of the previous layer. So each neuron, so the collection of all the neurons, what they are doing is computing linear combinations of the activations, the ages of the lower layer, and then adding a bias and doing that for each neuron in the layer. Okay, so this can be written compactly in this form. So this W matrix, the dimensions of the matrix are KL by KL minus 1, because I'm computing KL values from KL minus 1 inputs. Okay, so it's a rectangular or square. It can be a tall or a fat matrix. It depends on the relationship between, if the layers have the same number of neurons, then this is a square matrix, but it doesn't have to be. It can be whatever shape. Okay. And of course, BL is the number of the biases. So KL is the number of biases. Of course, it has to be in agreement with the number of neurons. Each neuron will have its own bias value. Okay, so now all we have to do after we compute the pre-activation, which is linear, is make it go through this nonlinear activation function, which could be one of many that we'll see in a second. And finally, at the output layer, now we're having these, again, the bold O, because I have multiple outputs computed as some function of the pre-activation of the final layer. Yes.
So, like, I'm just wondering here, what would happen if I don't use the same activation function
Oh, you can.
in all of them?
You can.
I can,
You can. There's no problem.
I mean, there's no problem, of course, right? Like you just, but
Here, I'm assuming it's all the same, but it doesn't have to be.
so what happens in that case? You know, of course, like when you implement this thing, usually you just write, I want, I don't know, like a value.
I have no way of answering. It
But-
depends on the problem. It depends on your task. It depends on the data. It depends on the architecture. This is just quite a kind of a template architecture. Then this will be instantiated in many different ways.
Yeah. Do you know if there's like some people who tried that?
Oh yeah,
Probably there
of course.
is.
Any modern network will have different activations in different places.
No. But I mean, like in the same layer. So you
Oh,
have
in the same layer.
like, for example, your first
That's a good
neuron
question.
has one activation function, the second one has like a different one.
No, not at all.
You know, because maybe it would learn like other sort of patterns or something like I don't know, I have no idea.
I don't remember seeing a network that has different activations across the same layer. That I've never seen. Maybe someone has.
I don't know. I think it would be interesting to
Yeah.
like, but yeah, okay. Well,
Yeah,
I
thank
was
you.
just curious.
No, it's a good question. I don't know. I've never seen it. Okay, so notice that there is an error in this picture. Okay, can you spot the error? What is the error in this picture? Assuming that I am computing probabilities of classes like this, which means that what function do I need to use? I need to use a softmax, right? And softmax is not a component-wise thing that you can compute. You cannot compute the output of softmax just by looking at each of the inputs separately, because you need the normalization. You need to divide by the sum of the exponentials. And so this cannot be written like this as independent blocks. So the softmax actually has to be a box that takes in everything together and produces a softmax transformation. It's not a component-wise. Softmax, hyperbolic tangent, sigmoids, ReLUs, all of those, they are component-wise. You can compute them separately for each input, but softmax cannot, because you need to exponentiate, but then you need to take them all together and divide by the sum of the exponential. So that picture is a bit wrong in that sense, but we've been lazy to update it. Okay, so why is this good? There's a very strong theoretical reason, because there's a theorem, it's kind of old actually, that says a neural network with one hidden layer and a linear output, but the activations of the linear layer of the hidden layer are not linear. Otherwise, it's just a linear function. So imagine, say, sigmoids for the hidden layer, and then just linear for the output. The simplest, it's a network like this. Why isn't it moving back? Network like this, but where the output is just linear. No activation at the output, as simple as it gets. Still, you can prove theoretically that with one hidden layer and a linear output, you can approximate arbitrarily well any continuous function, given enough hidden units. Of course, the trick is in the enough hidden units, because you may need a lot of them. Okay, so this is could be very expensive. So there are many results in this. So the field of mathematics that studies this kind of problem is called approximation theory. And there are decades of work in approximation theory. Okay, so this is a result from approximation theory, but which applies it applies beautifully to neural networks, and it provides this famous result. So this is a result from the 80s, from Sybenko, and then Hornick, Stinscombe, and White proved it also independently for many other activation functions for hyperbolic tangents. It was originally proved by sigmoid. It can also be proved for Gaussians. So a result like this applies to Gaussian radial basis functions. If instead of an increasing function, you have a Gaussian function that goes up and then down again, it also works. Of course, the caveat is that you may need exponentially many hidden units, depending on how complicated your function is. Okay, so there are many results in approximation theory. Another one probably you've known is that any continuous function can be arbitrarily well approximated by a polynomial. So this is the kind of results in the same type of nature. So just to give an intuition of why this is so think of a sigmoid. So each of these nodes here on the left, each of these is one of these, say, suppose we have a sigmoid function. So it's one of these logistic classifiers that we saw on Saturday. And I showed you a picture like that with these kind of sigmoidal shaped surface in 2 dimensions. I'm just in 2 dimensions, suppose that I have only 2 inputs, okay? And now when we have a layer of things like this, I'm computing different sigmoids in different directions in space. And there's a way to combine them to obtain a function you want. Suppose that the function that you want is that little bump over there. You can create it by combining 4 of these sigmoids in different orientations. If you add them with the correct weights, you get something that looks like that, okay? So this is the intuition behind universal approximation. And if you have a more complicated function, you need more of these. And you may need a lot of them if the function is complicated. So that's the problem. And that's why people don't use shallow networks with only one hidden layer, because to be good, it would need to be extremely large, extremely big. And there's learning problems too, but luckily there's a more recent work, more recent theorem, 2014, that says essentially that deeper networks with more layers can provide more compact approximations. So I'll show you in a second. So this is the number of linear, it's another way of seeing it, the number of linear regions carved out by a deep network with the inputs, depth, L, and K hidden units per layer. So it's a very simple network with this, all the hidden layers have the same number of neurons. There's L of them, and the width is D, so the input is D, as we have been using. So the number, now this is seen from a classification perspective, because when you do classification, you want to take your feature space and divide it into regions, different regions, depending on the classes. And what this theorem says is that the number of linear regions essentially grows exponentially with the depth, okay? So if you fix K and D, you see that this thing grows exponentially with L, which is the depth, okay? So if you have the same width and the same input, and if you put more layers, you get an exponentially more complex function that you can approximate. And so this is the sort of the theoretical result that supports going deep. And the paper that proved this first is that paper, is a paper co-authored by those people, Montufar, Pascanu, Cho, and Benju. Actually, Cho is one of our speakers. He will be here today, the 5 o'clock. He will not talk about this, but he was one of the authors of this very fundamental result in deep learning. Ying Cho. Okay, so any question? Now that we've seen the structure of a standard, of the standard model for what a deep network is. Now we're going to see how we're going to learn, while we learn them.
I just want to ask if these approximation theorems have also not only a theoretical meaning, or they also have strong applications in the constructions of models, or
This one, no.
Okay.
It's just it provides comfort that this kind of actually this the study of a very shallow network with only one hidden layer, which is very wide. It's a very active area of research, because it's much easier to understand what's happening. Actually, as I mentioned on Saturday, a very wide layer becomes almost the same thing as a kernel. Okay, and so you can study them using mathematical tools from kernel methods, reproducing kernel Hilbert spaces and all of that. So one of the reasons is that, and it connects with this in the sense that you know that if you're using an extremely wide layer, that layer has a universal approximation properties. So it makes sense to study. But in practice, I'd say no. They provide comfort. They explain why it's better to have a deep and not so wide network than to have a huge, very shallow but very wide network. They explains why it happens, but you don't use these theorems to design networks. No, they don't have much of a practical application, as far as I know.
Okay, and when you say approximate the function well in the first theorem, it means that for any epsilon exists a delta.
Yeah, that's this kind of thing. Yeah, I don't know exactly what the statement of the theorem is in terms of, but it's something like that. It for any accuracy level, I don't know if it's uniform approximation, uniform convergence. I don't remember, but it's kind of L2. It's integral of the square of the difference between the function and the approximation. And there are, of course, conditions on the function. It needs to be continuous, maybe it needs to be integrable too. Yeah, I don't remember the details of that theorem.
Thank you.
Wait. So just the people at home or back there.
What is the intuition why we cannot just use neural network with one hidden layer? So I mean, if we are able to approximate any continuous function with just one hidden layer, why we cannot just use neural networks with two layers?
Yeah, because of this theorem, because you may need a huge, if a function that you want to approximate, say if you're doing regression and the function is extremely complicated, you need a really, really wide network, and you don't know a priori how wide it needs to be. And if you use a deeper network, you have this confidence that as the depth buys you much more expressiveness, because the expressiveness grows exponentially with the depth. So you know, and if we, as we will see in a second in the history, what happened is that, especially for image classification, the networks became very, very deep, very fast. They have networks with 100 layers to get really, really expressive. And there's also theoretical results on the learning side, that when you learn them by back gradient descent, backpropagation, it's easier to learn a deep network than it is to learn with the same expressiveness than a very, very wide network and shallow. It's easier to learn.
Okay, but in theory, we can get like
theory.
large language model with one hidden layer.
In theory, well, the large language model is not exactly like this, right? It has the transformer and the attention. It has an additional level of nonlinearity in the fact that when you do the attention, you have this softmax multiply, which it also depends on the input, so that it's a more complicated thing. It's not just a feed forward, it is purely feed forward, but with more twists.
But if we can find some representation to be able to use it as a feed forward.
Yeah, assuming that you already have the embeddings.
Yes.
Because you cannot feed words to the network. You need them vectors.
Okay,
Yeah,
thank you.
in theory, yes, I would say yes. So maybe our brains is just a huge shallow network with a very large hidden layer. Any more questions on this part? No, I guess. Okay, so let's move on to how we learn this stuff. So as we've seen on Saturday, and it's true here again, we're gonna need to learn the parameters of the network, and we're gonna learn them from data, exactly as we did for linear models. So the typical words are training or learning. I don't like any of them. I would prefer parameter estimation, because I come mostly from signal processing, but okay, training and learning. The idea is to choose the parameters, and I will use this notation theta to mean all the parameters in the network, which in this case are just the weights and the biases. Of course, there are many other choices, right? As you know, there's when you have a network, someone, you or whatever, chose how many layers, how wide the layers are, what the activation functions are. All of this stuff needs to be decided, but I'm assuming that this has been decided before. I know it will work, and I'm just going to estimate the parameters. Okay, just the weights and the biases, nothing else. And so I am assuming I have, as before, a training set of examples, xi's, yi's, as we had on Saturday. It's called the training set. And I'm going to learn the parameters by minimizing the empirical risk, which you already saw, which is, as you remember, sort of a sample version. It's an empirical version of what you would really like to minimize, which is the expected value of the loss. But you don't have the joint distribution, you have samples, so you have to settle with the empirical risk and not the expected risk. And then maybe there's a regularizer that we have seen before also. Could be L2 norm, could be L1 norm, but there are other regularizers that we will see. So L is a loss function, which we already saw on Saturday. It's a function that measures. So this part here, is y hat I. So this f is the estimate of yi, and the loss function computes how much I should penalize a given estimate, y hat I, given that the true label or true value is yi. So this is called loss function. It could be square difference, it could be different things that we will see in a second. So omega is the regularizer, and lambda is the so-called regularization constant, which weights how much, which controls how much importance the regularizer will have. Okay, yeah. Oh, the mic.
What do we have a semicolon in the like computation function? Like,
Oh,
yeah.
yeah, no, yeah. Because it's sometimes people separate arguments. It's seen as a function that has arguments and parameters, and in a sense, the parameters are more fixed. The arguments are more change more rapidly. There's no real reason. It's just an arbitrary notation option. It could be f theta of xi. That would also be a nice notation. It could be f of xi and theta without the semicolon, like with a comma. There's no real reason why. It's just to kind of highlight that x and theta have different natures. One is the vector of parameters that controls the function, and the other is the argument of the function. That's the only reason.
Okay.
But it's arbitrary, like almost anything in notation. As long as it's clear, that's good. Okay, so as we've probably touched upon so I didn't have time to cover the optimization part in the Saturday lecture. So today we can look at that a little bit. And so, as you probably seen, most of you had some introduction to optimization sometime in your past life somewhere. In the course, gradient descent, that's how people do basically any optimization problem when there's nothing else you know how to do. If you don't have a closed form expression for the minimum, but if you can compute the gradient, then what you do is gradient descent. And you know that what the gradient of a function is. So anyone does not know what the gradient of a function is? I can explain in 30 seconds. Everybody knows? Okay. Sorry? Okay. So the gradient of a function is so you have a function that depends on several parameters and several arguments, so a vector of a collection of numbers. The gradient is a vector, which means it's a collection of numbers that, when seen as a vector in space, is pointing to the direction in which the function most increases. Okay, which means that the direction is the direction in which the function most decreases, if you look backwards. So if you are on a slope on your skis, do you ski? If you ski, you are on a slope on your skis, and the gradient is the direction in which the slope is the sharpest. It's going most down. Actually, that's the negative gradient. The gradient is the other direction. Okay, that's what the gradient is. So gradient descent is a very simple algorithm. It just does that. It iterates forever by doing the following two things. You choose a step size, and then you take a step of that size in the direction of the negative gradient. So you are at theta t-1, previous location. So think of theta as a vector in space, some position. So there's this space where theta lives. So there's theta I is over there, and the gradient of the function is pointing somewhere, and you're gonna move, so theta I-1, and the gradient points in this direction, so you're gonna move in that direction a certain amount that's controlled by alpha t. I'll have pictures about this in a second. Okay, so gradient descent is just this. You just need a tool that allows you some method that allows you to compute the gradient of this loss that we had in the previous slide, and a way of choosing a step size. And choosing the step size is extremely important, okay? Because if you choose a step size that's too big, suppose you're going down and looking for the minimum, there's a valley down there, there's the minimum. If you go too fast, you can end up on the other side of the valley rather than at the bottom, okay? And if you choose too small a step size, you're gonna go very slowly, okay? So choosing good step size, there's literally thousands of papers about gradient descent that just focus on the problem of how to select a good step size. Literally thousands, because gradient descent is a very old tool. It's not from last 10 years, like at least 70 years, or no, it's more, 100 years old. Okay, there are many ways to choose the step sizes. You need some stopping criterion. Let me just finish one. You need some stopping criterion. You need to know when to stop because you cannot go forever. And there are many ways of doing stopping criteria. One of them is just to look if the norm of the gradient is less than some quantity. Because if the norm of the gradient is less than some quantity, it means that you are in a approximately flat region, which is probably a minimum or close to a minimum.
Why do you, I mean, it's like just notation again, but why is there like this triangle symbol, which is not the delta,
Oh.
the delta is like this?
The gradient. I
Yeah.
thought you knew. Okay.
Why is it like the inverted
Yeah,
triangle
yeah.
instead of like the regular triangle?
Yeah. So
Which is what you
I thought
usually
yeah,
use
that's.
in this.
I forgot that we didn't cover everything. So I'm going to explain the gradient in detail. Okay. Suppose you have this function L, okay, of theta. Okay. And theta is a vector. In this case, in our case, it's, let's suppose like this. It's a vector of parameters. So there are parameters. In our case, what we're doing, this theta is the weights and the biases of the network, but let's ignore that. Let's just put them all together in one stack of numbers. Okay. Now, how do you raise like this? Okay, nice. So now, dl theta d theta I. Do you recognize this notation?
Yeah, I mean,
Okay.
so
Partial derivative
mhm.
of the function L with respect to theta I. So this quantity is how much L changes if I change theta I, one of these components, infinitesimally.
Mhm.
Okay. Now, if I do this, with respect to every of the thetas and stack them all in a vector. So the first component is how much L changes as you change infinitesimally theta 1 and theta 2 and so on, all the way down to theta d. Okay?
Yeah.
And this is what's called the gradient. This is, by definition, the gradient with respect to theta of this function L of theta.
Yeah, and
That's the upside down triangle.
Mm, but why is it like upside down? Like that's my question. Why is it not like this? You know,
Oh, that's a
like,
different thing. This
because-
is called nabla.
yeah,
It's a Greek word called nabla, and this is a Greek word called delta.
yeah, exactly. So why didn't you like just
Because
use,
delta
like,
is
so the-
used to represent the simplex, which we saw on Saturday. It's this, so delta is the set of all vectors that have non-zero components that sum to 1. That's a space of probability distributions. This is an operator. I don't know why they create. I don't know why it's historically why it's written like that.
Okay.
But it's the standard notation for the gradient, which is the vector of the partial derivatives of the function that you want to minimize with respect to each of these components.
Okay.
And so if you think of this vector in space, if you have some function, now I'm showing these, suppose these are the level curves. So suppose this is a mountain seen from above with the level curves. So the gradient, how do I change color? Nice. So the gradient is something like this. So this would be the gradient. If this is some point theta, this is the gradient of, it points up in the up direction, where the slope is the maximum. Where if you take a step in that direction, you would climb more height. Okay, and so what you want to do when you do gradient descent, because you want to find the minimum and not the maximum, is go in the opposite direction. Okay, is the notation clear?
Yeah. No, I mean, I'm just curious, to know like, but oh, yeah, what was the difference between like this and the Jacobian matrix?
The Jacobian, the gradient is a particular case of the Jacobian when your function L is scalar, has only just one number. So the Jacobian would be a matrix where you have the gradient. So if L is a vector value, if L has several components, it has several arguments, but it's only one number at the output. It's from RD to R. If it's RD to some R M,
Then you would
then you have a
like
matrix
proper
of
matrix
gradients
with,
where each
like,
column of the
oh.
Jacobian is a gradient of one of the components of L.
Okay, good.
Thank you. Let's go on. Okay, so this is gradient descent in one slide. So we want to apply these to the regularized empirical risk minimization, which we already saw. And it's common, just to keep the notation simple, to move the regularizer inside, because when I have 1 over n sum of n lambda omega, it's just the same as lambda omega because it cancels out. And because you can have this more compact notation as 1 over n sum across all the points of some local thing Li of theta. So this will be, it's written there, Li of theta is just the regularized empirical risk corresponding to sample I. Okay, you have a sum of these across all the data. You have n points and data points, say 1,000,000. This is a sum with 1,000,000 terms. Okay, now if you want to compute the gradient, fundamental observation is that the gradient of a sum is the sum of the gradients. Because the gradient, as you've all learned in your basic math, calculus, whatever, you know that the gradient is a linear operation. So the derivative of the sum is the sum of the derivatives. So the gradient of the sum is the sum of the gradients. And so if you want to compute the gradient of the whole thing, you need to compute the sum of the gradients for each of the data points, each of those Li's. Nice music. Okay, and this is very expensive. Okay, this can be extremely expensive if you have, because it requires a full pass over the data. So if you have 1,000,000 training points or trillions like we have these days, this is extremely expensive. You cannot do this. Okay, it would be extremely, extremely slow. Okay, so to the rescue, we have this other method, which seems that it is as the first time anyone listens to this, this is very stupid. This will never work. Which is you have 1,000,000 points. But instead of computing the gradient of the whole thing, you're going to compute the gradient with respect to only one point. Okay? You take the loss term that corresponds to only one of the data points, and you compute its gradient. You choose it at random. If you have 1,000,000 points, you choose one at random. That's it. Choose it. Interesting thing is that this gradient of one of the points is an unbiased estimate of the gradient. What does it mean to be an unbiased estimate? Its expected value is the true gradient, the sum of all the gradients. Because you're choosing one of them at random. If they all have the same probability, the expected value is just their average. And the average is exactly what we want to compute. So you know that the expected value of the gradient of the loss, if you choose one of the points at random, the expected value is the true gradient of the whole loss. Okay, this maybe looks like a great result, but it's not, because being right in expectation, you can be very wrong most of the times, and when you average, you have the right thing. There's no wisdom of the crowd in this case. And so, but it still works. It works very, very well. That's what everybody uses these days. It's not exactly like this, but I'll explain in a second. So what is stochastic gradient descent? It's a very similar thing to gradient descent, with only one small difference, is that you don't compute the whole gradient, you just compute the gradient of one of the terms in the average that produces the gradient. So you sample one of the points at random, okay, and you choose a step size, and then you take a step size in the negative direction of the gradient, but only for that point. You use only the loss function for that point. Actually, here I should have written to keep the same notation Li of theta, to be in agreement with the previous notation. It's these Li's. Okay. So here it should be Li theta. It doesn't matter. Okay, it's what's up there. Okay, so it's very simple. It's extremely simple. You just take one point at random, compute the gradient of the loss for that point, and take a step in the negative direction of the gradient. So there's many. One of the advantages of this is that what you expect. Each of these steps is much. So if you have 1,000,000 points, it's 1,000,000 times faster than a full gradient step, because you only need to compute one gradient, not 1,000,000 gradients. But of course, the algorithm will take many more steps to converge, because the gradients are noisy. And as I will show in a second in a picture. Yeah. Go ahead.
do that only once or?
No, you do it forever. You keep on doing it. It takes a long time. Yeah. Thousands and thousands of times. Yeah. Okay, so this is a very nice visual summary of, especially on the left side, by Gabriel Perret. So Gabriel Perret is a French machine learning mathematician guy who used to tweet every day. He would tweet some machine learning or math results. I think he stopped a couple of years ago or last year, but if you can still find him, it's worth it. So he has these very, very short visual summaries of important concepts, both in mathematics and machine learning. And on the left side, it's exactly what we've been talking about. So we have a function that's an average of functions on the top, right? Little f is an average of fi's. So the gradient is the average of the gradients, okay? Which means that, as seen in the picture in the middle, the gradient, the black arrow, is the average of the blue dotted arrows, okay? And what stochastic gradient descent does is sample one of these, okay? Sample one of these blues at random, and then take a step in the negative direction of that thing. Of course, the fact that they are on average, so the average of the blues is the black, it does not mean necessarily that the blues are pointing always in the right direction. There could be some blues pointing in this direction and still have the correct average, as long as the average is in the right. So sometimes you go in the wrong direction. So when I write stochastic gradient descent, I always say descent, quote unquote. It's not guaranteed that you're going down. Sometimes you go up, okay? It's not guaranteed. And the other version is the expectations. I won't go into that. But there's so this was Robbins and Munro have this theorem. This is from the, I don't know, late 50s or early 60s. That's not super relevant. Well, it's super relevant for this application because it shows that if a function is strongly convex, doesn't matter what this is. And now this is a very important aspect. And if the step size decreases, so to prove convergence with this method, you cannot have a fixed step size. Step size has to go down and down and down and down, which makes it sometimes go slow. But still, you know that it converges because the expected value of the difference between the true x, the true minimizer, and the minimizer that you get is going down as 1/k. It goes down very fast. Okay, so this method works for convex functions. Of course, the function that we're looking at is not convex at all, but it's still, if it didn't work for convex functions, then no need to worry. But it works for convex functions. Now let's hope it also works for other functions. In practice, you typically do not use just one sample. You use a so-called a mini batch of samples. So you don't sample just one of these points, you sample a group of them, say B of them. B is much, much less than N, say 100 rather than 1,000,000. And you, instead of computing just one gradient, you compute the average of the gradients in the mini batch. There's a question there, I guess.
On the first slide, was the series with K and 1/k?
Oh, in this previous slide?
Yeah.
Here?
Yeah.
What is what?
The theory, the
Oh,
K
this.
and 1.
Oh, this is sorry. I didn't map from one. So this is the step size. This is what I was calling. This is what I was calling alpha t.
Okay.
And this would be what I would calling in the previous slide theta t minus 1, and this would be theta t, and this would be li, and this would be theta t minus 1 to make the mapping. It's exactly the same expression as in the previous slide with different letters.
Sure, and the theory said it like the K is 1/k. What was that?
O of 1/k, it means that the error is going down the following way. The error, so so this is the true minimum. This is the thing that you're looking for. It's the location of the minimum of the valley. Theta xk is along the iterations. And what this means is that the difference between the two, so you can think of this as how far I am from the minimum, has a following expression. Some constants times 1 over the iteration count, which means that after one iteration, you go from this constant to 1/2 of the constant, and then 1/3, 1/4, it's going down as like that, geometrically.
Okay, so you mean K is also decreasing?
Tau k is also decreasing.
Okay.
The step size needs to decrease for this basic algorithm to converge. So you need to go slower and slower and slower and slower.
Okay, I see. Thank you.
Actually, you can go a bit faster if you know that the function is strongly convex, but that's not very relevant.
Sorry, okay, this works. Nice. I just wanted to ask if the stochastic gradient descent can help us like solve the issue of getting stuck in like local minimum or maximum.
Yeah,
Just a question.
yeah. Actually, stochastic gradient descent was first introduced as an inevitable thing to do because there's too much data and I cannot compute the gradients altogether. But then in years after that, especially in recent, like last decade, it was found that actually it is good that you do it like that because stochasticity adds the ability to escape from local minima. And because it has it's not so easy to explain. I had that in the other slides, which I didn't cover. It has an implicit regularization effect. Even if you don't have a regularizer, the fact that you use stochastic gradient descent sort of has I can explain it to you offline, as an implicit ability to regularize the problem because it forces the solution to have certain properties because it's being explored stochastically. Okay, so it's good. It is computationally more efficient because each step is much cheaper, and it has other added benefits that was sort of a surprise, but it does have those benefits.
Just an additional question has more to do with estimator theory. When you said that the estimator was unbiased on that slide,
Yeah.
why do we care that it is unbiased? Why is it that important or relevant?
Oh, it's extremely important because it means that if you do this many times, on average, you're going in the right direction. Because the average of the steps that you take, the average of the steps is exactly the step that you would like to take if you were able to compute the whole gradient together.
And
So otherwise you would be biased and you would be going in the wrong direction. So you go randomly because you have noise, but on average you're going in the right direction. That's why it's important that this is an unbiased estimator.
Okay.
So it's like if you're very drunk and you go like that, but on average you know the way and you end up at home. Okay, it's okay. So when we have mini batches, what we do is instead of just the gradient of one, actually I should have again the same change of notation to be compatible with the previous slide. This is Li of theta t. You compute not just one gradient, but a bunch of them, and you average across those B, let's say 100 gradients. And it's less noisy because it's an average, and it's still unbiased because it's the average of the same thing. So it's very easy to show that it's unbiased. And this is kind of the effect that it has. So batch gradient descent, so just standard gradient descent would be this blue line going there in the direction of the gradients, of the negative gradient. You go directly to the bottom. The purely stochastic gradient descent where you sample only one point at a time is the purple line that goes like really drunk guy walking around. But on average, it goes in the correct direction, so it ends up in the minimum. And the mini batch is something between the two. It's not as wiggly as the full stochastic. It's not as smooth as the full batch. So it's a compromise between the two. Okay, of course, adjusting the batch size is, again, another hyperparameter that you need. Sometimes you need to change along you start with if you have a very bumpy, if L has lots of local minima and it's very bumpy, it's good to start with a small batch so that you explore around a lot. And then once you know that you are not too far from a good minimum, then you can increase the batch size to make it smoother and to make it behave better. But this is all very hacky. Okay, so what do we need to be able to implement stochastic gradient descent or mini batch stochastic gradient descent or whatever? We need a loss function. Of course, we need a network that it is f, x, and theta. We need a loss function. We need the training set. We need to know how to compute the gradient of the loss function. We need a regularizer if we want to use one, otherwise we just don't use it. and we need to be able to compute the gradients of the regularizer. So we need all of these, okay? Because we need these to compute what we really want to compute, which is this gradient with respect to theta of L of F and xi and theta given by I. So I need to be able to compute these, okay? And I need to be able to compute gradient of omega. Okay, so let's see each of these in turn. Let's start with losses. Okay, so we'll look only at two losses. So the loss, the common loss for regression, we saw it on Saturday, is just squared error loss. We saw why it makes sense because it's computational tractable. It also has this underlying meaning that we are assuming that we have Gaussian noise in the data, but that's not very, very crucial. So our goal, of course, is to have the output of the network in this case, which is f of x and theta, being approximately equal to the desired response y that's in the training. So for a given training pair, x and y, I want that to hold as much as possible. Okay, so what makes sense to consider a squared error loss. I want to minimize the difference between y and y hat. Okay, so it makes sense. But you may ask, why not the absolute value? Why not something else? We've discussed that. So that's the one that people typically use. The real reason it's because it's tractable, because the derivative is very easy. Although there's other good excuses to use it. The real reason is that one, the other are just excuses. So let's, for later use, and I will warn you that this is not over yet, of course, let's compute the loss, the gradient of the loss, so the partial derivative, with respect to each of the estimates of y. So notice that I'm not doing just single regression. Single regression would be just estimating one value. I can think of reconstruction. For example, if you have an image processing problem, where you have an image that has noise, for example, and you want to produce a clean image, or you have a blurred image and you want to produce a deblurred image, you're predicting a quantity, a number of values, a number of pixel values. So the output of the network that does that has many different values. It's multi-dimensional. So it's not necessarily only one number. It could be a vector of numbers. And then just as I showed when I explained what the gradient is just a stacking of all the partial derivatives. So if each partial derivative with respect to, say, the jth component is just its estimate minus the true value, the gradient is just the difference between the two. So this would just be something like y hat 1 to y hat d minus y1 yd. So that's what we have in there. So that's the gradient of this loss. But notice, don't get too excited now, because this is not the gradient with respect to theta. What we want is the gradient with respect to theta. I don't want the gradient with respect to the input of the loss. I want the gradient with respect to theta. So, but we will need these, so keep it in mind. So this is not yet the gradient of the loss with respect to theta, which is what we want. It's just the gradient of the loss with respect to the predicted value. The other loss that is typically used and that we will consider is the cross entropy loss, which we saw also on Saturday, or the negative log likelihood, if it's the common choice for classification problems when we have a softmax output layers. And we have these scores, we apply the softmax, compute exponential of the scores, divide by the sum of the exponentials. That's a softmax layer, okay? So, as seen from a network perspective, the output of the network, what we've been calling F, is a softmax of the activation of the final layer. So remember that when we have L hidden layers, we have L plus 1 activations, reactivations. The final one, the L1 activation, is the activation that goes into the activation function of the final layer, which in this case is a softmax. Okay, so but to keep the notation simple, I just remove the L plus 1 and just call it Z. Okay, so the negative log likelihood, which we already saw on Saturday, which is the loss that we're using, is the sum across all the classes of the indicator of the class. So that 1 C equals I, Y is 1 if C equals the true label and 0 if it's not. Okay, which means that if I want to minimize this quantity, I want to maximize the log of the output of the network for the correct class. Okay, that the only case where this is, so this is actually the same as This quantity is exactly the same as log Fy of x theta. Okay, but just to keep it general, we write it with the so-called one-hot encoding notation to call it the cross entropy. Okay, and this can be written like that. This is what I was saying. It's minus log of the softmax, because the output of the network is a softmax, but the component y of the softmax. Softmax is a vector with all these exponentials normalized. I take only one of them, the one that corresponds to the correct label. Okay. Intuition, of course, if I want to reduce the loss, I want to increase the value of the softmax is assigning to the correct label for a given sample. Obvious. Now, to compute the gradient, I'm not going to do it in detail, but if you compute the gradient of the loss with respect to z, not with respect to theta, with respect to z, which is the activation of the final layer, reactivation of the final layer. After some manipulation, which I won't show you, this is the same as, is the softmax for the class with respect to which I'm computing the partial derivative, minus 1 if this is the correct class, or minus 0 if it's not the correct class. Okay? What's the intuition between this gradient? It gives you the following thing. If C is not Y, if I'm computing the gradient with respect to the pre-activation of the wrong class, okay, this gradient is positive, which means that because you're going in the negative direction, you will try to decrease the value of the softmax for wrong classes. Okay, because this is the gradient, and I'm walking in the negative direction of the gradient. So this gradient is pointing for wrong classes, it's pointing in the direction of trying to make these values lower. And for the correct class, so dl dz if c equals y, for the true class, this gradient is negative because softmax is always a number less than 1. When you subtract 1, you get a negative quantity. So it means that the complete gradient is doing the following. It's trying to increase the probability of the correct class and decrease the probability of all the other classes. Okay, which makes sense. This is exactly what I want to do. I want the network to give high probability to the correct class and low probability to the other classes for each sample. Any question? Yeah. No. Yeah, you can interpret them as probability, you can interpret them as estimates of the probability of the class.
Minus some of the
Yeah.
probabilities,
Yeah.
log probabilities, and I'm a little bit confused because here we are not really manipulating real probabilities. So
No, yeah, this is just a formally equivalent to a cross entropy. If you interpret the indicator 1 as a probability distribution, which it is because it's 1 at one point, it's 0 everywhere else, so it's a probability distribution. It's the probability that in that training example, the class is that class. You can interpret it like a probability because if you assume it's true, then that's what it is, okay? The other one, there's a big discussion around if you can interpret these softmax outputs as probabilities. Typically you cannot, because they're not calibrated. And I would need to explain what calibration means, which I have no time. But it's not, you can kind of interpret them as probabilities, but they're not really probabilities.
yeah, so a loss like cross entropy does not be calibration.
Sorry?
It does not
No.
apply calibration.
No, it depends. If you're doing just logistic regression with a linear model, and it depends on the assumptions that you make about the data. Okay. Here we have, I explained on Saturday when we talked about logistic regression, if we saw that logistic regression, so the use of the softmax, as some underlying assumption of how the labels are generated. And here we have real data. The assumptions are all wrong. Every assumption is wrong. It's just sometimes it works well. There's a very famous sentence by George Box. All models are wrong, but some are useful. This is useful, but it's wrong. You cannot. It's strictly speaking, it's not a probability.
Okay, thank you.
So again, as in the previous case, this is not yet the gradient that we want, which is with respect to theta. I don't care about I care because I will use it. What I really want is the gradient with respect to theta, but that I have not found out how to compute yet. Okay, so we have the loss function that we've seen, two different loss functions. What we need next is a procedure for computing the gradient of the loss function with respect to the parameters, which we probably will see after the coffee break. Is that a good time now? Yeah? Okay, so any questions you may ask, and then we stop for the coffee break. Yes, there's a question here. Yeah.
Yeah. So here we are sort of like, if you think about it, like we're sort of defining everything like in the negative, in the sense that, so here we are talking about a loss, like I make this much error when I predict, etc. But why do we necessarily have to define it like that? Like, couldn't you just measure the similarity and try to optimize for like the maximum? I mean, it's the same, but wouldn't it make like more sense?
This
Like-
is just one way of doing it. There's many other ways of solving machine learning problems. There's sort of, for example, k-nearest neighbors, which is based on similarities, but it's a very different route.
But maybe my question is like, why did it end up being like a loss instead of like I don't know, like a gain or something like that? You know, like
Oh, it's the same. You can call it a gain, and instead of minimizing, you maximize it.
but I mean, like what I mean is like, why? Like, who came up with the idea of, oh, you know, because if I invented this thing, I would have.
It comes from
used-
decision theory, because to formalize, all of these are decision problems. You want to decide the value of the parameters. You want to decide what a label is. And to formalize decisions mathematically, you need to come up with a way of saying how good they are. And one way of saying how good the decision is to assign a quantity that measures that and try to solve the problem by minimizing or maximizing. If you see it as a loss, you try to minimize the loss. In economics, for example, a lot of people talk about utility, and instead of minimizing the loss, they maximize the utility. But you need to somehow get a handle on what optimal means, and all that always goes through some function that measures how good things are, and that's where losses come from. It's not the only way.
No, no, of course, of course. Wow, thank you.
Okay. I hope the coffee was good and the posters and everything. So just before we continue, I was just informed by, sorry, I forgot her name. She's sitting there. Thank you. That actually Gabriel Pere is still posting actively this kind of stuff, but just not on Twitter or X. He's posting it on Blue Sky. So if you want to know more about this kind of stuff, but you can go on X and check, because there's a huge collection of really nice posts like this. So don't miss it. And yeah, and another thing that I realized that I probably hadn't explained super well, but I'll try to explain it when I get there. Yeah. Okay, so here is where we were. Okay, so we had just seen that we need to have these data set loss functions. We've looked at the two standard loss functions that people mostly use: squared error loss, cross entropy, and how to compute the gradient of the loss function with respect to the argument of the loss function, not with respect to the parameters. That comes next. That's done, and now we need to find a procedure to compute the gradient of the loss function with respect to the parameters themselves, which is what I'm interested in, because I want to minimize the empirical risk and maybe also the regularizer with respect to the loss function, with respect to the parameters, I'm sorry. And so this is now famous, is the workhorse of modern machine learning, gradient backpropagation, okay, and autodiff, and we'll see what this is. So the goal, of course, is to compute the gradient of the loss function for a given. Notice that I'm always looking at the problem of computing the gradient of the loss function for one data point. But that's enough, because if I'm doing stochastic gradient descent, I just need one of these at a time. If I'm doing full batch gradient descent, I need all of these to average. If I'm doing batch, I need a few of these. So this is the fundamental thing that I need to be able to do. Compute the gradient of the loss for one data point with respect to the parameters of the model. And this will be done by the gradient backpropagation algorithm, okay, which is nothing more than the chain rule for derivatives. It's just the loss, the gradient of the loss with respect to the function is the gradient of the loss with respect to the score times the gradient of the score with respect to the parameters. Of course, this is just the high-level view. This will have to be seen in detail, okay? So it's just a chain rule of derivatives, which is written there in different, in standard notation. So if a function h, say, is the composition of a function f with a function g, so f of g of x, then the derivative of h with respect to x is the derivative of f with respect to u when u is equal to g of x times the derivative of g with respect to x. So it's kind of intuitive. You have a composition of two functions. The derivative of the final one with respect to the input of the first one is how the final one depends on its argument times how this one depends on the input. Okay, I'm sure most of you have seen this in a calculus course in your first year of any STEM course. So this is the chain rule for derivatives, and that's essentially all there is in the gradient backpropagation algorithm. It's just complicated versions of this. So here's an example. Suppose this is nothing to do with machine learning, just some simple example to illustrate the chain rule for derivatives. Suppose you have this function r, which depends on t, but it depends on t through these two intermediate functions. One of them is t squared. The other one is 3t plus 1. Of course, I can simply compute r, which is t squared times 3t minus 1 plus 1, and then compute the derivative of that. That's easy to do. But to illustrate the chain rule for derivatives, we're going to write it using that thing above, noticing the fact that if some of those functions, so for example, g could be a vector valued function. In this case, the intermediate function that I have, so I go from t to this middle layer, and then from this layer to the output, and the middle layer is actually a vector valued because I have two numbers there. I have u and v, okay? So when I go from t to u and v, I need to compute some two derivatives. When I go from u and v to r, I'm actually computing a gradient because r has two arguments. So there will be an argument, the derivative of r with respect to u and the derivative of r with respect to v are the two components of the gradient of r with respect to u and v, okay? So by putting these all together, we have that the derivative of r with respect to t, so the derivative of the above node, the node above with respect to the node below, is the derivative of r with respect to u. So how r depends on u here, this comes from here, times how u depends on t. Plus, so this is one, this thing here, this first term expresses how the things change on this side, and what is this? Blue, red. It's on what happens on this side, okay? So it's the derivative of r with respect to v times the derivative of v with respect to t, okay? So that's it. This is gradient backpropagation in one slide. That's all there is to it, okay? Yeah. Doesn't matter. This is true, still true.
So if we
I'm gonna check if it's correct. Yeah.
but the derivative of multiplication is
Yeah.
the derivative of u
Yeah.
multiplied by v.
Yeah. There you go. So the derivative of r with respect to u is v, right? The derivative of r with respect to u, this is v, right? Because r is u times v, okay? Derivative of r with respect to v is u, okay? The derivative of v with respect to t is 3. The derivative of u with respect to t is 2t. So, okay, so there you go. When you put all of that together, you get 2tv plus 3u. And then you know that u equals t squared. You put everything together and you get the final derivative, which is correct. Okay, so this is gradient backpropagation. Okay, now we need to use these for our purpose of computing the gradient of the loss with respect to the parameters of the network. But the network has not only parameters, there's other quantities in there. Okay, and they all depend on each other. The activation, the pre-activations, the activations, the weights, and the biases, they all depend on each other. And so we need to proceed carefully. Just again, this picture is slightly wrong because this could not be a component-wise thing, but let's forget about that for now. Okay, so recap. The pre-activation of the final layer is a linear combination with this weight matrix W of L plus 1. So for any, not for the final layer, for any layer, it's this weight matrix W multiplied by the activations of the layer below it plus the biases. Let's compute the gradient of the loss with respect to the activations of some layer. Okay, to compute the gradient of the loss with respect to the activation of some layer, I need to compute the partial derivative of the loss with respect to each of the activations. Okay, so I'm computing this partial derivative with respect to each of the activations of layer L. I mean layer L. Okay, and what we're going to do simply is, this is exactly an implementation of this expression in the previous slide. Okay, sum this on the bottom, sum of all the products of the partial derivatives that make up the dependency that you're looking for. So here you go. You need to sum across all the i's, all the pre-activations, the gradient of the loss with respect to the pre-activations times the derivative of the pre-activations with respect to the activations of the layer below. Okay, so notice that this is kind of a to have a kind of an intuitive view of why this is okay. It's kind of like these. It's kind of like this cancels out with this. Okay, that's kind of the intuitive view of when you multiply one derivative with respect to something times one derivative of that thing with respect to something else. It's like they cancel. You're not canceling anything, but if you want to look at the expression and get a feeling for what if it is correct, then you should look for this kind of cancellation. Okay, so now the first one is just whatever it is. It's the derivative of the loss with respect to the pre-activation of layer L plus 1. But the other one, it's very easy to know because the other, we know from the expression above that the pre-activation of layer L minus 1 is a linear function of the activations of the layer before. Okay, if you look above, if you look at this expression here, you immediately know what this derivative is, this one here. Okay, the zi is just the derivative of the ith component of zl plus 1 with respect to the jth component of hl. And because one of them is a matrix times the other, this derivative is just the corresponding component of the matrix, right? So if you want a more detailed view, then I have no time to do it as detailed as in this one. So for example, if you have here zi at layer L plus 1, this is just z L plus 1. This is W L plus 1, which is, let me actually write it, is a matrix. And you have H, say J, L. Okay, this is H, L. And so the derivative of, I don't know what this is asking for. Okay, the derivative of this guy with respect to this guy is just a corresponding component of the matrix. It's just W ij of L plus 1. Oops. I was too excited. This is the first time I'm using this app. Okay, so this is Wij over there. Okay, let's go on. So in compact notation. Those are the partial derivatives, stacking all the partial derivatives in a gradient there. We have the gradient of the loss with respect to the activation of the layer L is matrix WL plus 1, so the weight matrix that connects layer L plus 1 to layer L, times the gradient with respect to Z. So these gradients here, when I stack them, I get this gradient over there. The gradient with respect to Z L plus 1 of the loss. So this tells you how you go from computing the gradient of the loss with respect to the pre-activation of a given layer to the gradient of the loss with respect to the activation of the layer below. Okay, they are related through the weight matrix. That's one thing we need. Okay, next. Now remember that the activation of a given layer is just the activation function applied to the pre-activation. Okay, say sigmoid or whatever. Okay, so now that will allow us to do this observation that the derivative, the partial derivative of the loss with respect to the pre-activation of a given layer, okay, is the derivative of the loss with respect to the activation times the derivative of the activation with respect to the pre-activation. Again, look for the pattern that shows that this cancels with this. Okay, so the derivative that's left is the one that we want. There's no cancellation going on. Huh? This is not a mathematical cancellation. It's just a pattern that you should look for to check if the gradients are being computed correctly. And of course, because H and Z are simply related through these component-wise functions, say sigmoids for anything or ReLUs or whatever, the derivative of the activation with respect to the pre-activation is just the derivative of the activation function. Here, this one, because of this operation here, this derivative is just the derivative of the function. So it's quite simple. Which means that the gradient of the loss with respect to the pre-activation of a layer is the same as the gradient of the loss with the activation of that layer times the gradient or the derivatives of the pre-activation computed at the pre-activation value. Okay, now we can look at what these derivatives look like. Okay, depends on the activation function that we're using. If we're using linear activation, the derivative is just 1, so there's nothing. If the activation layer is linear, this is not here. This is just gone. There's nothing here. It's multiplication by 1. If the activation function is this sigmoid, then it's easy to compute the derivative. So the sigmoid, the e to the a, well, written like that, 1 over 1 plus e to the minus e, so the logistic transformation for in one dimension. The derivative looks like that. It can be computed in closed form. It's very simple to compute the derivative of that. It looks like that little bumpy thing, which shows that the derivative is maximum when you are close to 0, which means that when the output is close to 1.4 to 0.5, and it goes to 0 at the ends, which means that in this sense of activation, the derivative is most active when you are near the boundary between being above 0.5 or below 0.5. For hyperbolic tangent, you can also compute it. So not surprisingly, it has sort of the same shape because the function is sort of the same shape as a sigmoid. It's actually a sort of a sigmoid, but it's a shifted and scaled sigmoid. So the derivative looks sort of the same. It looks a bit like a Gaussian bump, but it's not Gaussian. It's the square of the hyperbolic second. The only thing that the key message is that whatever activation function you use of these, the derivative is very easy to compute. It's known in closed form. And finally, for the ReLU, if we ignore the fact that it's not differentiable at the origin because it has a step, the derivative is 0 almost everywhere except it's 0 when you are below on the right for negative arguments and 1 when you have positive arguments. It's a step function. Ignore the fact that it's not differentiable at the origin. Actually, it has a subgradient but no gradient, but that's not an issue. Okay, so depending on what the activation is, we plug one of those functions, one of those derivatives here. Tuk, tuk. Okay, let's go on. We're not over yet. Now, gradients of the loss function with respect to the parameters. Now, those are the ones we really care about. We need the others because these ones will depend on the others, because these are the ones we want. We want to compute gradients with respect to the parameters. So, recap, the pre-activation of layer L, this we've already seen these, is the weight matrix that connects layer L to layer L minus 1 times the activation of layer L minus 1 plus the bias. When I compute these, so the gradient of the loss with respect to the weight matrix is the gradient of the loss with respect to the pre-activations times the derivative of the pre-activations with respect to the W's. Okay? But now this is kind of dual of what we had before. Before we had gradients of Z's with respect to H's, I get W's. When I get derivatives of Z's with respect to W's, I get H's, right? The derivative of Z with respect to H is W. That's seen from far away. The derivative of Z with respect to W is H because it's a product of the two. Okay? So let's see it in detail. Again, let's look for the pattern that we always look for, which is these cancels with these, so it's the correct product. So the derivative of the loss with respect to the elements, each element of the weight matrix of the Lth layer is the derivative of the loss with respect to the pre-activation times the derivative of the pre-activation with respect to the corresponding parameter. But that derivative is easy, it's just Hj. Because of the linear, if you again write, I think it's gone, it's not here anymore. Yeah, it is actually here. Now, when I was computing the derivative of Z with respect to H, I get the corresponding element of this matrix, right? Now, when I'm computing the derivative of Z with respect to the element of the matrix, I get the corresponding H. Okay, so that's because it's a product of the two. The derivative with respect to one is the other one. Okay. There we go. So I know how to go from computing the derivative of the loss with respect to the pre-activation to the derivative of the loss with respect to the parameters of the network, of the weight in this fact. So if I put all together, if I stack all these gradients in vector notation, I get the gradient of the loss with respect to all the elements of the matrix, weight matrix of a given layer, WL, is equal to the gradient of the loss function with respect to the pre-activations of that layer, outer product with the activation of that layer. Okay, let's unpack a little bit this notation. Notice that this gradient here is a gradient with respect to a matrix, not with respect to a vector. So it's a matrix itself, okay, with the same structure as W, and at each position it has the gradient of the loss with respect to that entry of the matrix. So it's a matrix of the same size as W itself, okay? So it has it's KL by KL minus 1. It is matrix, okay? Now, this gradient here is the gradient of the loss with respect to Z, but Z is a vector, okay? So this is a vector. So this is a vector that has the same size as Z, okay? And this one is also a vector, same size as Z2. Of course, as Z of the previous layer, or L, they are the same size, okay? But it's transposed, so it's like this, okay? So as you probably remember from linear algebra, when you multiply a column matrix by a row, column by a row, you get a matrix, okay? It's called the outer product. So this derivative, this gradient of the loss with respect to a matrix is a matrix that is obtained as an outer product of a gradient with respect to Z times the activations at the previous layer, okay? So if you don't remember your linear algebra very well, this is what it is. You can just try to remember how you multiply two matrices, and when the matrices have this kind of shape, you get a matrix that has as many rows as the element of the first vector and as many columns as the element of the other vector. Not to be confused with the other way around, which is when you multiply some vector v by some vector u, like this, you get a scalar. This is r. If you multiply, if you do it the other way around, you get a matrix. It's the outer product versus the inner product. Is it clear? Good. We're almost done. Similarly, for the gradient with respect to the bias, the gradient with respect to the bias is very easy because we go up there and we see that the gradient of z with respect to b, the derivative of each component of z with respect to each component of b is just 1, because it's just added there at the end. Okay, there's nothing else. So there's nothing here because there's a 1 over there, which comes from this derivative here. In the case of b, when it's computing the derivative with respect to b, it's just 1. Okay, and so that's why there's nothing there, but we can leave a 1, which makes it clear what's in there. Okay, so how do we use all of these? Notice that we've been through 3 slides that have different types of derivatives. Derivatives of losses. Let me just recap. Derivative of losses with respect to activations. Derivative of losses with respect to pre-activations. Derivative of losses with respect to parameters. And they all depend on each other, okay? And so putting it all together, it turns out to work in this way. So this is the backpropagation algorithm in one slide, okay? So you go from the output of the network to the input, okay? You go in backwards. You start at the output because the output is where the loss is. The loss is computed with the output. So if you begin by computing the gradient of the loss with respect to the pre-activation of the final layer, which we saw before the coffee break, that in both in the case of softmax or squared error loss has that form. It's just the output. Remember, it's softmax minus 1. Okay, so in this it's not exactly like that. It's very similar. For regression instead of y, we had like y itself. The gradient of the squared error loss is just the response minus the desired value. That's it, because the loss is the square of the difference. When you compute the gradient, it's just a difference. For classification, for the softmax case, we had these. It's the softmax, all the softmax vectors, the vector with all the softmax values, minus 1 at the correct label and nothing for the others. We saw this just before breaking for coffee. Okay, so we have this gradient of the loss with respect to the pre-activation of the final layer. And then now you loop going backwards. So you start at L plus 1, which is the final layer, and go all the way down to layer number 1. And you compute the gradients of the parameter. So the gradient with respect to W of the loss, we already saw that it's the previous thing we saw. It's the gradient with respect to Z times H. Okay, there you go. Gradient with respect to Z times H. But the gradient with respect to Z, when little l is L plus 1, comes from the first row, from the first line. Remove all these. So we know how to compute that. And the gradient with respect to the bias is just the gradient with respect to the pre-activation. And then next, what you do is you compute the gradient of the hidden layer below with respect to the hidden layer below. So you compute the gradient of the activation of the previous layer is the matrix, the weight matrix, times the gradient with respect to the pre-activation. But this one you already have to, because it comes from the first row. And now this is where the change happens in terms of when you move to the next layer. Now you need to compute the gradient with respect to the pre-activation of the previous layer. This one you don't have yet, but we know how to compute it. It was in one of the previous slides. It's the gradient with respect to the activation, which you have. You just computed it in the line above, times this. I forgot to explain what this means. Everybody knows what this means? This is the Hadamard product, or the component-wise product. When you have two vectors multiplied with this symbol, it means that you're multiplying the corresponding components of the vectors one by the other. So A, B, C, and C, D, E, you have A times B, and so on. So it's just a component-wise product between two vectors. So we had this in one of the previous slides. So we know exactly how to compute Z, the gradient with respect to the pre-activation, ZL minus 1. We just computed it using that expression. And now this is the end of each turn of the loop. When you go up to the 4, And you need to compute now the gradient with respect to the parameters of the layer below. It's no longer big L plus 1, it's now big L. Those gradients with respect to Z that you need here, in the first iteration, they were computed up there. In the subsequent iterations, it's being computed here. Okay? So it always, everything works out well. Okay? So this can actually be written in a much more compact way by using something called a computational graph, where you can see these. So you can see these layers of in a very compact graphical notation, the layers of the network, that the thing that you're manipulating is this graph that has, so in this picture, we have parameters in blue and variables in red. What the graph does is take an input, there's a forward pass from the bottom to the top, where each of those little blocks, what it knows how to do is to take the inputs and compute the output, which is a function of the input. For example, the output of this block, what this block does is take X, multiply by W, add B, that's it, that's Z1. And then from Z1 to H1 is just applied some nonlinearity, sigmoid or something. What is not showing? I'm not drawing. Yeah, I was not drawing. I was just pointing. Yeah, but the pointing is okay. So what this block does now, okay, what this block does is take the inputs, these inputs, and computes Z1. We already saw it's W1 times X plus B1. Okay, that's Z1. And then H1 is just G of Z1, where G is, say, ReLU or something. Okay, and then there it goes. Okay. So this operation of taking the inputs of each of these blocks in the graph and taking the parameters and the variables and doing this computation is called the forward propagation or forward method. And in software, in code, this is sometimes called the fprop, forward propagation, where you compute the output of a box given its input. So it's what I was saying. This is just kind of obvious. And so by calling these fprop methods in each box in the right order, you need to compute it from the bottom to the top. In this case, from the input to the output, you get what's called a forward propagation step in the algorithm. Okay. Now, what is beautiful in modern software implementations of these is that you don't really need to know how to compute the gradients that were shown in this algorithm. Okay. This is all done automatically for you. It makes you lazy. Okay, so this backpropagation is also implementable in this modular way. It's essentially the same graph, although sometimes you represent it backwards. So each of these boxes essentially should know how to do the following. It receives the loss gradient, the gradient of the loss with respect to its output, and it knows how to compute, how to update, how to take that gradient and compute the gradient of the loss with respect to each of its inputs, which is what it needs to propagate backwards. Okay, so it's written precisely there. So each of these boxes needs to have this method, computes the loss gradient with respect to its parents, given the loss gradient with respect to the output. The parents are the inputs. Okay, this is what it needs to know how to do. Okay, so each method, of course, all of these needs caching. Of course, when we run the backpropagation algorithm, we need to assume that the forward path has already been computed, and this age and z's are all computed. Okay, they need to be there. And so calling the bprop method in reverse order, starting from the output and going all the way back, all the way down to B, it's called the one backpropagation step. Of course, it only needs to reach the parameters. You don't really need to reach X, except in some specific applications that I will talk about later on. So we don't need to compute the derivative with respect to X, because X in principle is fixed. Okay, I'm not going to this. This is what you're learning in the afternoon labs. All of the modern software toolboxes do these for you, mostly for free. I was told that this is a bit outdated. Some of these are old. Nowadays it's almost exclusively PyTorch and JAX, right? There's anything more interesting? Yeah. Okay, so we saw loss functions. We saw how to compute the gradients of the loss with respect to everything, namely with respect to the parameters, the thetas, the W's and the B's. And now next we're going to see the regularizer and its gradients. Actually, we're going to see a regularizer that's not of this form in a second. So remember, maybe I haven't explained carefully enough what is a regularizer. So regularizer is, so we have this term on the right, which is the average of the loss functions across the data. And the regularizer is a function that you add to the empirical risk to try to encourage the estimate of the parameter to have certain properties. Okay, if you don't have a regularizer, if you do not use this, if you take this away, you're just trying to force the network to explain your data as well as possible and not asking anything else. Okay, if you add, because this is an optimization problem, if you add this extra term is also trying to be minimized because you're minimizing the sum and you're giving it more or less importance depending on the weight that you put on it, the lambda. Okay, and you may use these to encourage theta to have certain properties. One of the classical ones will be to have not a too big a norm, to try to avoid theta from having very large values. And you do that by using a norm, say norm squared, that we saw on Saturday. But you may want to encourage other things. So this is where you bring in knowledge about some, if you have some knowledge about what you know about the parameters, maybe you can put it in these regularizer. And there's many, many ways of doing it. I will just look at this, two of the standard ones. Okay, so we will look at L2 regularization. Just add the square of the norm of all the parameters to the loss function. L1 regularization, which we talked about on Saturday, which is sometimes called lasso, because it encourages sparsity. And dropout regularization, which does not have that form. It's a form of regularization, but it cannot be written as adding a regularizer. It's something different. Okay, so L2 regularization. Okay, first of all, you don't regularize the biases. Okay, the biases are left alone. You let them be whatever they want to be. You want to regularize the weights because, in a sense, the size of the weights. Think of a polynomial fit. Okay, which is a good example for intuition. The coefficients of a polynomial. The size of the coefficients kind of tell you how wiggly the polynomial is. If the coefficients are small, the polynomial is kind of smooth. If the coefficients are very high, the polynomial is very wiggly. Or if what a linear transformation like W is, if W has very strong values, it means that there are some directions in which there are very strong derivatives. So the function changes very abruptly, very fast. So you want to keep these weights not too large. And you typically do that by adding the sum of that there's a compact way of writing just the sum of the squares of all the weights in the network. The sum of the squares of all the elements of all the matrices. That's all. That's all that is. You can actually have different weights for different layers. You can do many, you can improve the sophistication of these arbitrarily, but this is the simplest version. Okay? It's equivalent to a Gaussian prior on the weights. We already saw that. And the gradient of this regularizer is trivial because it's a square. 1/2 of a square, the gradient is just the matrix itself. So it's very, very simple because the derivative of 1/2 of x squared is just x. Okay, I guess you all know that. And so what happens when we do gradient descent with this? So this is a 3-line derivation, very simple. So the gradient descent says, take your current W and take a step of size eta in the negative direction of the gradient of the loss with respect to this W. But the loss has two terms, as you remember. It has this term, which is the empirical risk, which I don't care about now, and this regularizer term. Okay? Now, this gradient, we already saw it's up there. It's just W. Okay? So when you put everything together, we see that what the gradient descent update looks like is take your current W and multiply by 1 minus eta times lambda, which is here. Okay? W minus eta times W again. It's 1 minus eta lambda times W. Minus the gradient of the loss. Okay? So what does this show is that when you're using this kind of regularizer, and now you combine it with gradient descent, right? What happens is that the form that each step takes is the following. You take your current W, you multiply it by a number which is less than 1, so you shrink the matrix a little bit in all the coefficients in the matrix, all the parameters in the matrix decrease by this little factor which is slightly less than 1. It would be typically like 0.999 or something, 0.9. It shrinks a little bit. And then you subtract the gradient of the loss term. Okay, so this closed form update for W under the L2 norm is what gives the name of these, the reason why this is called weight decay. Because the weight is decaying a little bit, you have the weight, it shrinks a little bit, and then it moves in the direction of the gradient. Okay, that's why it's called weight decay. Notice that even if you are at a minimum of the loss term, so even if the second gradient is 0, if you keep on iterating, this W will go to 0. Okay, it will decay all the way down to 0, even if you are at a minimum of the loss. So there's this decaying effect of this loss. The other thing that you can use is L1 loss, L1 regularization, which is just the sum of the absolute values of all the parameters in all the matrices. Okay, this is known as, in some contexts, lasso. It's equivalent to Laplacian prior. It doesn't matter this. The gradient is, we saw it already. The gradient of the absolute value is the sine function. If for positive values it's +1, for negative values it's -1. So that's the sine function, ignoring the fact that it's not differentiable at the origin. And it promotes, I will not explain why, but just keep in mind that it promotes sparsity. So it encourages some of the weights to be exactly 0, okay? Even after a finite number of steps. The other form of regularization that's very often used is something called dropout, okay, which does the following. So that's the network. And what this does is the following. At each iteration during training, or by each batch or whatever, there's multiple ways of doing it, you force some of the nodes to have 0 activation. Okay, you kind of stop them from influencing what's the rest of the network. Okay, and now you learn like this, and you change the number, the subset of nodes that are deactivated changes randomly from iteration to iteration. Okay, that's what's written there. During training, remove some hidden units chosen at random. Apparently, this was proposed in like 11 years ago by some very famous people. You have Hinton there and Alex Krichevsky, the AlexNet guy. Actually, this was used in, I think it was used in the AlexNet paper. I'm not sure. Ilya Sutskever, all famous names. Yeah. Oh, there.
Sorry, I just wanted to ask really quickly, why sparsity seems to be always a kind of a goal?
Not always?
I see it like mentioned a lot, and I
Yeah.
think I haven't understand why it's always a goal, basically.
It's not always a goal, but it's often a goal. Because if there's sparsity, if you train a model and you have a good performance in the end, you get, say, good validation results on that model, and the model has a lot of 0 parameters, it means that those parameters are actually not needed. And so the model is actually simpler than what it looks. Although you have 1 million parameters, if 900,000 of them are zeros, only the other ones are being used. The problem is that you don't know a priori which ones. If you're interested in that topic, just Google lottery ticket hypothesis, which is a nice and interesting.
So kind of the ideal regularizer will be the one that penalized the irrelevant like parameters, kind of made them 0, basically.
Oh.
No.
But you don't know a priori which ones are the irrelevant ones.
Exactly, but the ideal regularizer would do that, would increase the sparsity of the irrelevant.
Yeah, if you knew which parameters are irrelevant, you could just start remove them from the beginning, and just keep the others. But you don't know, right? So.
Okay, thank you.
Okay, so.
Can I ask you?
Sure.
Can you please go back to the slide of weight decay? Yeah, why the red quantity is less than 1, and can be
because
also
both eta and lambda are typically very small numbers.
Okay, so we choose then.
Yeah. The step size is always small, and lambda is also always small, of the order of 10 to minus something.
Okay, and this quantity needs to be also
Otherwise, there's
positive.
no decay. Sorry?
Needs to be also positive or can be negative.
No, if eta and lambda are very small, so eta and lambda are positive.
Okay.
So otherwise, you would be the regularization effect would be the opposite. You would be trying. So if lambda was negative, it would try to encourage omega to be big rather than small. Okay, that would make much sense. And eta is the step size, so it's a size. You assume that it's positive, and because you want to go in the direction of the negative of the gradient, not in the other direction. And typically, for these things to work, both eta and lambda are pretty small numbers. So
Okay,
that's why I said the 1 minus eta lambda is typically something like 0.9999 or something like that.
Okay, so it's between 0 and 1.
Between 0 and 1, yeah.
Okay, thank you.
And close to 1, typically. Not much smaller than 1. It's just slightly smaller than 1. Okay, so what's the idea behind dropout regularization? There's been a lot of discussion around it. So the way it was sold when it was proposed is something like prevents hidden units from co-adapting to other units. So it prevents that some node relies too much on some of the nodes in the previous layer and not on others. And because it will, in a sense, by sometimes turning off some of the nodes below, each node will be forced to not rely only on a subset of them and try to spread its dependency from the previous layer from all the nodes. So it kind of prevents co-adaptation, okay? And that's supposed to be something good. And empirically, dropout works quite well. It's very used. It was used, it's been used for 10 years now, and with a lot of success. So this is a detail that I'll probably skip for now. Yeah, I will skip this. Okay, so how do you change backpropagation? How do you change backpropagation without dropout to backpropagation with dropout? It's extremely simple. There is a mask. There is a binary mask at each layer that zeros and ones chosen randomly with certain probability. And then when you're doing all these updates that we saw, you change the activation of the previous layer that's being used there by multiplying it by the mask. So some of the components will be zeros, the others not. The others will be whatever they were. And down here, when you compute the gradient, because you want to prevent these updates to depend on ages from the previous layer that are zeroed, you also multiply it by the mask down there. So you have a binary mask M associated to layer L minus 1. You multiply age by the mask. I could have put there explicitly. I wrote includes mask, and you multiply by the mask down here. So including dropout in the backpropagation algorithm is typically, it's very, very simple. And all the toolboxes for deep learning have dropout options everywhere. This is all done for you. You don't have to worry. You just have to worry if you want to understand. Okay, some tricks of the trade. Not that I'm the best person to talk about tricks of the trade because I'm not much of a practitioner. So biases, initialize at 0. Weights, you cannot initialize all the weights at 0 because that would not work. For example, if you have hyperbolic tangent activations, everything would be 0. It would be stuck in 0. It would never work. So you cannot initialize all the values, all the weights to the same value, although they would essentially all have the same gradient and they would all move in the same direction together. So you have to do some randomness. There are many ways of doing initialization. There's many tricks, many hacks. Sampling around 0. There's some very famous thing called Gloro initialization from 2010, which has these, I don't know if some of these people who have more experience than me in coding that can explain why this makes sense. I never looked at it in detail. I know it exists and I mention it, but it says some trick. For LU activations, sometimes it's good to initialize with a slightly positive quantity so that you don't have too many nodes on the left side with 0 gradients. So try to push things a little bit to the right. So there are lots of tricks. So making these things work, that's what you talk about in the afternoon labs. Our monitors have a lot of experience. They know much, much more than I do about this stuff. So hyperparameter tuning, I'm told these days that don't worry about it, just use Optuna. I don't know if this is fair. data normalization aspects, decay learning rate, choosing mini batch sizes, adaptive learning rate. So learning rate is also seems to be a black art. Gradient checking, debugging on small sets. I had a student the other day was trying to develop something and was complaining that he's I hope he's not listening. He was complaining that don't tell what it is. That is every time he tried something, he needed to wait for a week for the model to train. And I said, but how many data points do you have? I think 28 million. Why don't you just train on 28,000 to see what happens? That you can try 10 things in a day rather than wait for a week for everything you try. So start with small data sets. And these days, of course, there's much better optimization methods than the standard gradient descent. So I'll briefly mention this kind of direction of work, which starts with the idea of using momentum. So momentum it's an idea that comes from physics, right? You have a particle that's moving and the particles have momentum, the mass times velocity, or inertia if you want. They want to keep moving in the same direction. And momentum is just that idea that rather than just do a standard gradient update, which would be like this, right? You move the parameter vector so I'm using G to mean some gradient estimate. It could be the full gradient, it could be a single sample from stochastic gradient, it can be a mini batch, it doesn't matter. Okay? You're moving in the negative direction of the gradient with some step size. This is a standard gradient descent or stochastic gradient descent. With momentum, you actually add to this direction of movement, which is the negative gradient, another vector with some weight, which is the direction of the previous move. It's like the particle is moving, it has some inertia, it sees the gradient, and it doesn't just go in the direction of the gradient. It goes into some combination of the gradient and the direction it was coming from, okay? And this seems to be empirically, and it's easy to show why, extremely useful, and it makes the algorithms go much faster. For example, notice that if you are here, suppose you are here at this point, okay, and you were here before. So this is theta t minus 2, this is theta t minus 1. Okay, you just did this move in the previous step. Okay, now this is these lines that you see below are level curves of the objective. So the gradient in this point is pointing in this direction. The gradient is pointing in this direction, right? But the previous movement is pointing in this direction. I'm just carrying this red vector and moving it there. And so what the particle, let's imagine that the parameter estimate is a particle, is going to move in some linear combination of these two vectors, which turns out in this example to be in this direction. Okay? And so it won't greedily move just looking at the gradient because it would oscillate a lot. Without momentum, this thing would just go. But with momentum, it kind of gets the feel for where the things are going and will go much faster to the origin. Okay? So there's a lot of papers, a lot of theory, a lot of work on momentum. It's been used I think it was invented in Russia in 1950 something by Polyak, and the original name was the heavy ball method, which is a nice name. So adaptive gradients. So Dushi, Hazan, and Singer around 14 years ago. So the idea is that it makes sense to use separate. Why we need to use a step size? So this parameter vector theta has many different things inside. Biases, weights of different layers. So why should we use the same step size for all of them? Doesn't make much sense. So this idea of using an adaptive step size, which rather than just a number, it's like a diagonal matrix if you want. It's a vector of weights, okay? And the idea is to use separate step sizes for each component. So for each component, theta t, you see, we'll use at iteration t, we'll have theta j of t. It's the jth component of theta. Okay, and so the algorithm works like this. Instead, there's this expression now is for gradient descent, but as seen component by component. I'm not giving the expression for the whole vector, but I'm giving you the expression for component j, one of the components of theta. It's the same component that previous iteration minus something multiplied by the corresponding component of the gradient. But now this something is some step size alpha plus this other thing, this g, the square root of g. And this g will control how big the step size is for each component. Okay? And the way it does so is by computing a sum of the squares of the gradients that it has seen. Okay? What this does is a component that has seen many very large gradients. This g will be large, and so the step size will decrease. So a component that has moved a lot will be slowed down. Okay? Conversely, a component that has not moved too much because the corresponding gradients have been very small in these previous steps will have a relatively smaller value of g, and it will move faster. It will try to increase its speed. See, I'm moving very fast in that direction, I need to slow down. I'm moving very slow in that direction, I need to move faster in that direction. Okay, so this is what this is trying to do. It's more robust to the choice of the step size. It's more robust to different parameter scalings. It's more robust to many different things. There's a big drawback, which is G never decreases because it's a sum. It's a total sum of squares of gradients, and sum of squares is always something that always goes up, which means that the method is always slowing down. Just some directions slow down more than others. Okay, so because of that, it was very easy to solve. It was never published. It was presented by Jeffrey Hinton during a lecture, and it became very famous, no need to publish, which is RMS prop, okay? So the idea is that the expression is exactly the same, but you may ask, why is this epsilon over there in the denominator? Though this epsilon is here just to make this thing numerically more robust, because if G is very small, close to zero, this becomes very large and it's numerically unstable. That's the only reason. Forget about epsilon, it's not critical. So, very clever. What it does is the following. Instead of simply adding the square of the gradient, you actually do some sort of decay in G. You take the previous G and multiply it by some number less than 1. So you decay it. And then you add 1 minus lambda, 1 minus gamma square of the gradient, which means that even if you are in regions where the gradient is essentially 0, G is going down. And so the step size for that component is going up. Okay, so if you are in a region of the loss function that is very, very flat, the algorithm speeds up in that direction because it can go fast because it's pretty flat. So this was proposed by Hinton, I think 2012 or something, or 2013, something like this. Again, same advantages. And then there's Adam, which is kind of mysterious. So it's the state-of-the-art method. Well, it's not a state-of-the-art method. It's the kind of the pattern, the template for the state-of-the-art method. So it's an amazing success. They published this paper in 2015, 10 years ago this year, and it has more than 220,000 citations. So there's almost no no deep learning paper that doesn't cite Adam. It's kind of a standard. And it combines aspects of RMS prop and momentum. So what it does is uses this type of, it computes separately sort of a moving average of momenta, and a moving average of step sizes of V's and M's using the same technique. So it's a weighted average between the previous momentum and the gradient, and a weighted average of the previous V and the square of the gradient, okay, as in the previous methods. And then there's some correction because forget about it. And then the update is essentially the same as in Adegrad and the RMS prop, okay? It's very successful. It works very well. And no lecture about basics of deep learning would be complete without mentioning Adam. It has some drawbacks, has some problems. There's hundreds of papers following up on these and doing improved versions and explaining theoretically why it works and all of that. And finally, we'll save the final half hour for convolutional neural networks, which is actually the ones that made neural networks great and famous, with AlexNet, which was a convolutional neural network. These are the type of neural networks that are closer to the neural inspiration that comes from the brain, especially from the visual system in the brain. Okay, so how is a convolutional network different from a standard network? Not very much. It's just a neural network with a special connectivity structure. Okay, I told you I hate the word neural, but I've fallen into this trap. I'm always saying neural networks. Okay, so convolutional networks have so-called convolutional layers. Who does not know what a convolution is? Everybody knows what? No one doesn't know what a convolution is? Yeah, fantastic. Better than the usual students. What is different between a fully connected layer and the convolutional layer? So the first convolutional neural network was arguably Fukushima's network from 1982. I think none of you was born then. Maybe most of you. Yeah. So this is a Japanese researcher. And so it was inspired by the Hubel and Wiesel work on visual system of mammals. And it's this, I'm not going to explain what it does, but it has essentially the same structure that modern convolutional networks is, the basic structure. And this one, which is much later, so 98, I guess by then many of you, well, some of you were already born. This is Jan LeCun, 1998. I mentioned it right at the beginning of the talk. It's that thing that he did when he was at AT&T to recognize digits. And it's the idea is that rather than in a standard deep network where all the pre-activations in one layer depends on all the activations in the previous layer, here we're dealing with structured data. It's not, you cannot look at it just as being a vector of numbers. It's actually an image, typically. And so image have spatial information. The information is structurally spatial. And so it makes sense that you look locally. When you're processing the image, it makes sense to look locally because most features in images are local features. And so this is the inductive bias that these networks have. I will not explain this one in detail. I will explain what convolutional layers are in detail. Who knows everything about convolutional layers and wants to skip this? So no one. You do. Some people do, I'm sure. Okay, so what is a fully connected layer? Suppose you're processing images, very small images. These are from Feifei Li's slides. Very small images, 32 by 32 by 3. So it's a color image. So you have 32 by 32 pixels, but each pixel has 3 numbers, RGB. So it's a color image, suppose. To do a fully connected layer, this is the same as you stack all these numbers, which are 3072 of them, you put them in a vector, and then there you go. It's a standard linear operation. You multiply these by a matrix. Suppose you want the next layer has a dimension 10. You need this matrix that has 10 by 3072 weights, okay? And the result is just a collection of 10 numbers. So this will be a fully connected layer for this structure of an input. All activations depend on all the inputs, okay? I'm ignoring the activation function just for now, okay? Now, in a convolutional layer, it's very different, okay? Suppose you have the same image, 32 by 32 by 3, and now you have, rather than a fully connected layer, rather than a big matrix, you have this little structure, which is sometimes called a filter, which can have different sizes, but in this example, it has size 5 by 5 by 3. So imagine this little box, and now imagine that you put this little box here, overlapping. So you have these 5 by 5 by 3 again, and you compute the inner product between the two. So you take, so this 5 by 5 filter is a little box. This little box has 5 by 5, that's 25, times 3, that's 75. It has 75 numbers inside, okay? And so you take those numbers, you put them on top of the image, you multiply each of the numbers in the filter by the corresponding number in the image, and you add everything. You compute the inner product. It's the sum of the element in the filter times the corresponding element in the image, you get a number. And then you slide it by 1 pixel to the right and do the same, and another pixel and do the same. And you do that while you can fit the filter on top of the image. So in this case, you would do it 28 by 28 times. Okay? Because you cannot allow the box to go outside of the image. Not for now. Okay? So there you go. So you put the box on the image, you have the 32, the image, the filter, you get one number as a result. The result of taking a dot product between the filter, the elements in the filter, and the small 5 by 5 by 3 chunk of the image. And you get a 70, so the filter is a 75-dimensional dot product plus a bias, which you can write like that. And then you keep on shifting, you do it for all possible positions, and you get an image of size 28 by 28. Okay, which is the convolution of these. This is called this operation is called a convolution. Okay, it clear? So this is what a convolutional layer does. Why is it 28 by 28 and not 32 by 32? Because the box cannot go out. You would need it to go out and be a little bit outside to have a 32 by 32 result. So you have a 28 by 28 result, which is essentially 32 minus 4. Which is 32 plus 5 minus 5 plus 1. Now, instead of one filter, you may use several filters, okay, and compute these several times, okay? This would be equivalent in a standard fully connected layer to not have just one activation, but several activations. You're computing different features of what comes before. So to do that, for example, you can use, say, 6 filters, not one. And each of these filters, so this is essentially a repetition of this image 6 times. You get 6 activation maps. There you go. Okay, you have a convolutional layer with 6 activation maps. So you transform an image of 32 by 32 by 3 into sort of an image of 28 by 28 by 6. It's like if you have a 28 by 28 image with 6 color channels. They're not color channels, they're sort of feature channels. They're extracting different properties from the image, but you can think of them as colors if you want. So some important names here are stride. The stride, as the name implies, is how much you shift every time you compute one of these inner products, and then you shift. I said you shift by 1, and then by 1, and then by 1, but it's not necessarily so. You can shift by 2 or shift by 3, depends on what you want to do. So in the previous example, the stride was 1, I was shifting by 1. Number of channels is the number of filters that you use. In this case, number of channels is 6. And then it's very easy to compute what the sizes are. So if you have an n by n image and you have filters of size f by f, and the stride is s, the resulting image is the size m by m, where m is n minus f divided by s plus 1. It's very easy to understand. So these are just a couple of examples, which I will probably skip. And then if you're not happy with this fact that the result is smaller than the original image, because of the fact that you cannot take the filter outside the image, one way of solving this is something called padding, which means adding zeros around the image so that now you can go all the way to the corners and all the way to the boundary and still have a valid convolution. Yes?
There are standard practice on how to pick a stride. Like, for example, you just basically pick one. Because, like, let's say if there was...
You need to try. What works best for your problem. It's so problem dependent that there's no general answer. Okay, why is it called a convolution? Well, maybe you all know, because this operation, as seen from a mathematical signal processing perspective, is called a convolution. Yes.
Yeah, I imagine that maybe like something else that you can do instead of like just putting zeros like in the borders of the images, like maybe you can go to the other side and put
you can. Instead of padding, you can assume periodic boundary conditions. You can imagine that the image lives in a torus. And so when you reach the end, instead of putting zeros, you use pixels from the other side of the image. But both of them are artificial, because outside of the image, there are no zeros. And outside of the image, it's not a good idea to think that the neighbors of these pixels are the pixels on the other side of the image. So both are very artificial. They're mathematically convenient, but none of them corresponds to anything that makes real sense. But you have to do something. It depends on the problem. It depends on what you want to do. One really nice way to do it is to consider that there is something outside that you don't know, and that you want to estimate it too, and you put it also in the things that you're estimating, like the weights. And then you can solve the problem. You can attack the problem as estimating the weights of the network plus the padding as an unknown. It's much more difficult to do, but you can do it, and people do it when dealing with these problems for image restoration. Okay? That's what really makes sense, is to treat the outside of the image as unknown, not as zeros or as periodic boundaries. Okay, so in one picture, we can immediately see why this is extremely economic in terms of parameters. So if I have these two layers, a very simple, with only four variables in each layer, a fully connected layer will have 16 parameters, connecting all the four to all the four. A convolutional layer with a filter of size 3 has only 3 weights. So in the left, we have 16 parameters to learn. On the right, we have 3. Okay, it's much smaller because there's this structure. So the assumption that you're going to use convolutional layers is a form of inductive bias. Okay, we talked about it in the beginning of the lecture on Saturday. So inductive bias is some knowledge about the problem that you bring into your approach that somehow you force it into the method that you're going to use. And when you use convolutional networks, you're essentially saying, bringing into the problem the knowledge that you have, that it doesn't matter where the features are. If you're looking for faces, it doesn't matter where the face is. So the features that you extract need to be the same independent of the location of the image. And so this shift in variance is what's being captured by convolutional layers. Actually, that's what I'm going to talk about. I'm going to skip the padding. It's not very interesting. We can just illustrate it in one dimension. So in one dimension, if you have this image, say, this little image or this little vector 15142, and you convolve it with this little filter 1 minus 1, 1, you get only a 3-dimensional thing. You go from 5 to 3. If you add the padding, in this case, 1 is enough, 1, 0 at each side. You do the convolution, you get something which is again dimension 5, but you shouldn't trust too much the end values, because they actually have the influence of what you put in the padding. You say you put 0 padding, why not 1 padding? Why not once? Or why not replicate the final, why not another 1 and another 2 on the other end? There are many options, okay? And none of them has really very strong support. Okay, so the fact that you use convolutions equips the network with these, at least these layers have this property which is called shift equivariance. So keep in mind that equivariance and invariance are different things. I will talk about invariance in a second. So equivariance means that if you have an image and you convolve it with some filter, you get some result. If you shift the image and you convolve it, the result is the same shift applied to result as it was applied to the original image. So equivariance means that the way the input changes is reflected in the same change in the output. It varies in the same way. That's why it's called equivariance. Okay, it has this, so it's a form of inductive bias because it equips the network with this property of being equivariant to shifts. Okay, so for example, if you're detecting faces in an image, you want your method to be equivariant. If the face shifts, you want the result to shift equally. Okay, you don't want the face to be detecting someone else. The other important thing is that convolutions can be used for many different types of data. Okay, 1D signals can be used for text. Noah will talk about it tomorrow a little bit. It can be used for other types of sequences like stock exchange, stock returns, many different scientific signals of all sorts. It can be used for images, 2D images, like standard images, spatial distributions of data. It can be used in 3D, which could be point clouds for LiDAR. It can be used for video. It can be used for medical imaging volumes, which are 3D but don't have time, like MRI volumes. It can be even for graphs. You can define convolutions on graphs that are not necessarily arrays of pixels. So it's a very general, the idea of convolution is extremely general and very applicable in many different areas. Now, as I said, do not mistake equivariance with invariance. Okay? Equivariance means you apply some transformation, and after the operation that you're interested in, you want this transformation to have to be replicated in the result. So for example, you have a cat and you scale it. You want the result of the convolution to also scale accordingly. But invariance means that if you apply some change, you want the result to be the same. So invariant means don't change. And equivariance means change in the same way as. Okay? So for a classifier, for example, of course you want invariance. You don't, if you're detecting cats, if your goal is to say if the image has a cat or not, it doesn't matter where the cat is. You just, if you shift or scale or rotate the cat, you all just want the output to say cat. That's it. So equivariance is not the same as invariance. So whereas convolutional layers have equivariance, pooling layers have invariance. Okay, and what is a pooling layer? A pooling layer is an operation that takes a layer, and typically an image, but not necessarily, but typically an image, and produces a smaller image by using the values in some window and doing some operation with it. It could be average, it could be max. So in this case, in this example, it's called max pooling. What the image, the smaller image you have on the right, each of the pixels is the maximum of the pixels on the corresponding colored block in the original image. So for example, in the top left corner, you have 1156, the maximum is 6. The other, on the top right, 2478, the maximum is 8. Okay, so this is max pooling. Takes a bigger image, produces a smaller image by taking windows and looking for maxima inside those windows. It could be average pooling. There are many other types of pooling. Max pooling is probably the most common one. And why does it provide invariance? It does not provide full invariance, but it provides some level of invariance. Here's an example. Suppose you have that image which is all zeros, except that little structure with the ones, this little upside down L or something. And now there's the filter up there. You multiply, I'm going to compute the convolution with that filter. Okay, there you go. And then I'm going to do 3 by 3 max pooling. Okay, and then if you look down, so after doing the convolution, well, the result of the convolution is the blue circles down here. Because the filter is 2 by 2, the image goes down from size 4 by 4 to size 3 by 3, and you get those 3 images. And now if you do max, if you look for the maximum, say you're doing 3 by 3 max pooling, no matter where the shape was, the final result will always be 3. Okay? Of course, you may say, wow, this is a very contrived example, very small shift, very big window. But of course, yeah, there's no guarantee that it's invariant. If that one would change to a different position, if it went out of the box, then you lose invariance. Okay, if you look around, there's lots of more elaborate examples. So, for example, this is an example. You have this bar in 2 different locations, and then you're just doing max pooling with some size 2 by 2 max pooling. And we see that as long as the bar does not cross the boundary of 2 windows of which you're doing the pooling, then obviously nothing changes. Okay, and you can create examples for invariance, for rotation, where you can rotate some shape and still have the same output, or scaling. You have this shape, you scale it down, and you get the same output. So max pooling buys you some sort of scale invariance, shift invariance, rotation invariance, although just a little bit of it for each layer, just a little bit of it. And so I already said this. You can have multiple convolution filters. Okay, so given all of these, it's pretty hard to understand exactly what a convolutional network is doing, because it has a lot of these. So a modern convolutional neural network has convolutional layers, followed by pooling layers, followed by more convolutional layers, followed by more pooling layers, some dropout layers. So it's a big mess. Okay, so it's complicated. We can analyze very clearly what each layer does, but it's very hard to have an intuition for what everything is doing together. You can think about it for a while, but okay. So let me look more carefully, just because it's a nice example, at these at AlexNet and the ImageNet moment that I mentioned at the beginning. So the full ImageNet dataset is this huge dataset. It was created by Fei-Fei Li and her group, I think in 2010, initially 9. It has 14 million labeled images, okay, which is a huge effort. It was using Amazon Mechanical Turk. It has 22,000 classes, okay, organized hierarchically. This is it was a huge effort. Oh yeah, sure.
Yeah, so about convolutions, what types of filters are typically used? Because I don't
What
know.
mean type?
I mean, what do you do when you filter? Like, what do you
You
look
learn the
for?
filter. You don't choose the filter. You just choose the size of the filter.
Oh, all right.
So the filter, the filter, the weights in the filter are exactly the W matrices that we had been seeing before. And so to learn this, you do gradient backpropagation with respect to these weights, with the constraint that they need to have this structure. Okay, that's all. So you don't choose the filters. You learn them.
I would just like to add that computer vision before deep neural networks was deciding what these filters would be. A lot of it, and
Yes, exactly. Yeah. So most of computer vision before CNNs, a lot of research was deciding what these filters look like. People use wavelets and different sort of representations for the images. Now you learn the representations. Sure.
Thank you for the presentation and for the things. So actually, for filters,
Not over yet. 5 more minutes.
Don't we have some strategies to initialize the filter and then train the filter?
Yeah.
Okay. So we don't just choose them randomly. We have some strategy or options just to initialize. Okay.
Yeah. And then, of course, the issue of choosing the sizes and how many and all of that, you need to search. So that's why this is very expensive to do, because you need to try different options and you need to do something called architecture search, which is try different architectures and see what happens. Yeah. Okay. So a very large data set with lots of categories. So actually the categories are organized hierarchically. For example, there's a category of carnivores, which contains the canines, which contains the dogs, and the dogs have the working dogs and the Siberian, blah, blah, blah. So it's a very complicated structure. So it's a very hard classification problem. But there's the small version, which has, I think, 1.2 million images and 1,000 object classes. And it was typically divided. There's several tasks. One of them, 1.5 million images for training, 50K for validation, and 100K for testing, and so on. Okay, so this is AlexNet. So AlexNet was this famous network from 2012 that I mentioned at the beginning, and it has this kind of structure. It has 54 million parameters. So it's convolutional. It has 8 layers. 5 of them are convolutional. The final 3 ones are fully connected, so they're not convolutional. But notice that now it's not so serious because the final layers are much smaller in terms of spatial size. It was trained on these 1.5 million ImageNet images. They used 2 GPUs for a week, okay, which corresponded to 50 times speed up over the CPUs of the time. Remember that this is 2011, 2012. They use dropout regularization. I think it's the first appearance of dropout regularization. And the test error was 16.4, which we saw before. Actually, so next we have, not many years after, this is like, I remember, it's like 3 years later, we are already up to, I don't know, this is like 15 or 12 or 20 something layers. So this is GoogleNet. It's much smaller in terms of number of parameters, but it has many, many more layers. So it's kind of taking advantage of the fact that you get the same expressivity by going deeper, although this is very hacky at this time. So a few years later, this idea of residuals was proposed. So the residual is essentially the idea that you can add kind of shortcuts that go in parallel to the layers and that simply copy the input of a layer by 1 or 2 layers ahead. Okay, and then you add with some weight. Okay, this is called a residual layer, or sorry, a residual connection. It was proposed in 2016, and the key motivation was something that I haven't talked about, which is vanishing gradients. Okay, you can imagine that if you're computing gradient backpropagation in a structure like this, okay, you have the loss at, I don't even know where the end is. Yeah, the end is on the right. you have a loss there. And remember that you need to propagate the gradients, and propagating the gradients means multiplying gradients by gradients by gradients by gradients backwards. When you multiply by so many gradients, that when you're computing gradients with respect to the parameters back here, you have multiplied by so many things that the probability that it's all going to be zero is very high. That's called vanishing gradient. Or if it happens that all these gradients are bigger than 1, if you multiply many of them, then it explodes. So there's this issue called vanishing gradient or exploding gradient, which is very hard to handle because you may be it's very unstable. It's a long product of things. So they need to be very carefully kept, not very far from 1. Otherwise, it will explode or go to 0 very fast. Okay, that's a well-known problem in implementations. And the fact that you use these skip connections help control these, because it's kind of, you have the gradient, when you're doing back propagation, the gradient is propagated not only through the layers, but also directly through this sort of shortcut, this skip connection. And that helps mitigate this vanishing gradient problem. Okay, so there's an explanation down there. Instead of just products of gradients, so if you have 10 layers, the gradient with respect to the parameters of the first layer is a product like that, d 10 times, okay? But now if you have a way of adding a constant, a fixed number to that product, then this stabilizes this propagation. Because with residual networks, people created really crazy big networks. This was 2014, not long after. So VGG, this is actually VDG19 is, I think the date is wrong. Oh no, VDG19 is not the year, is the number of layers, 19 layers. And there's very deep networks up to 150 layers or more than 150 layers for imaging problems. Another very interesting observation. This is a paper by Tom Goldstein's group from 2018, is that, I think this is the first time I showed this picture, but it's an interesting picture. This is kind of a depiction of what the loss landscape looks like if you project it down to 2 dimensions. So this is the loss, the thing that you're trying to minimize, the empirical risk. In this case, it's a 2-dimensional picture, so you imagine that you have only 2 parameters. It's just in 2 dimensions. But this is not actually that. This is a 2-dimensional projection of actually a loss in very high dimensions. It's actually a ResNet 56, which has millions of parameters. And what happens to the structure of this loss function when you use skip connections is that it goes from looking like that to looking like that. It's vastly simpler and vastly easier to optimize. So that's one mathematical explanation I'm just hand waving of why these skip connections and residual connections seem to work. And of course, there are many other architectures which I will not talk about, transformers, namely. This, in a sense, can be seen as CNNs with adaptive weights that are adapted on the fly. They will be covered in another lecture. I will mention in the end when. And in the interest of time, I'm going to skip the final part. It's only a few slides. Well, I can say what it is. So the fact that we can compute gradients with respect to, remember when we had this computational graph, I said, we don't need to compute the gradient with respect to the input because the input typically is fixed. But actually, you have the ability to compute the gradient with respect to the input, and that may be useful for some tasks. One of the tasks is visualization. Okay, you may ask the question: what is a network like this that is learning how to detect faces or whatever? What is it learning? What are the filters do? What does it think that a face look like? Okay, and you can do that by doing the following thing: you force the label at the output to be, say, in the example that I'll show, banana. It's an object detection that classifies fruit, banana, and then ask, what is the input that maximizes the intensity of the label banana? And you do that by gradient backpropagation. You fix the label and you compute backpropagation to the input, and you do gradient descent not on the weights, but on the inputs. And you try to find an input that maximizes the strength of the label banana. And this is an example. This is what it is. This is what this is quite old, from 2015, but this is what, I don't even know what network it is, thinks that the banana looks like, sort of. Okay, You can also specify inner layers. You can do many. So this is a very hot topic these days, even for language models, to try to poke into the system and see what concepts are stored in that. It is the beginning. Another thing for which this can be used is for adversarial attacks. For example, you can have an image that's being correctly classified as, say, horse or ship, and then you compute the gradient. You want it to be classified as something else, okay? And you force the label to be that something else, and you compute the gradient of this new label with respect to the input, and you look, what is the pixel that has the strongest gradient? And you change just that pixel. And in some cases, just by changing that one pixel, you can change the label, okay? Those are some examples where the true label, for example, this is a horse. This is an old example too. A horse, just by changing that one pixel, it became classified as a frog, okay? And you can actually, there's very interesting example, it's a very interesting work, where rather than changing an image, people actually built an object. This is a plastic turtle in 3D painted with a texture that was learned to be detected as a rifle, as a gun. So you show this little turtle to object detection software, and it says it's a gun because it was learned by that, like that. And there's this very interesting work. The same group that has this visualization, which is a sweater that you can wear, which fools face detection. You don't need to cover your face. You just need to wear that sweater, and the sweater prevents your face from being detected. Okay, it's called an invisibility cloak. Okay, and you can buy the sweater. It sells these sweaters. Okay, more to come in updating lectures. This is about to finish. So we covered the very basics. It's just scratched the surface of the basics of deep learning. There's much more in upcoming lectures, mainly connected to this, that could be seen as continuations of this one. So Noah Smith tomorrow will talk about language models and how we use these kinds of models for language. Transformers and large pre-trained models by Sveta Agraval on Thursday. And deep learning for vision and language by Desmond Elliott on Friday. Okay, and if you want books, here are 2 recent books that are good comprehensive coverages of deep learning, and thank you very much. And if there are questions, I'll be glad to answer. But everybody wants to go.